Today we are going to discuss about Doppler's effect, and through Doppler's effect we will understand about redshift, okay, redshift and blue shift. So when those big stars run out of energy, okay, so they collapse and they form black hole. So Hubble's law also explains that the universe is expanding when planets are located closer to the sun. They are going to orbit at a faster speed. Today we are going to start the science and technology module, and in the science and technology module, basically like today it will be an introduction session, and I'm going to discuss about the let's say physics and astronomy related topics. All right, and we will go as per the let's say like previously planned schedule. Okay, so basically like when we talk about the science and technology thing, so we need to understand which areas of science and technology are important for the prelims exam, and then after we have understood about the areas, then we will also understand about relative weightage of science and technology. Then we are going to talk about these topics. I'll take you through the previous year questions also. All right. So here when we talk about syllabus of science and technology, in the prelims exam basically they have included the keyword general science. Okay, what? They have included the keyword general science related to science and technology. And when we talk about the weightage of science and technology, so generally the questions are 10 to 15 questions per year. Every year they ask about 10 to 15 questions. And why there is higher weightage of science and technology? It is because, let's say like, for science and technology, one thing is, let's say it's important for the UPSC prelims exam, and also it is important for the IFOS examination, Indian Forest Services exam. And as you know, the cutoff for Forest Services exam is much higher as compared to the cutoff of prelims exam. And Forest Services exam is taken by people who have science background. So generally questions from science and technology and environment and ecology sections are higher in the GS prelims exam, because GS prelims is common for civil services and it is common for forest services also. All right. So this is the weightage of science and technology. So if we see 2014, 2024, 23, 22, 21, okay, like more than 10 questions every year. So 13, 12, 12, 14, 10, like that. Okay, so it has been more than 10 questions and about 15 questions every year. So this is the weightage. Okay, so if you talk about 15 questions means 30 marks in the paper. So it is important that we all should be very, very concerned about science and technology. I mean, like we should take it as an important subject for the, let's say like, for the GS paper. Now, when we talk about this particular slide, so here we are going to discuss about the areas that are important from science and technology section. Okay, what areas are important? So let us discuss about science and technology section. So these are the areas from where generally UPSC asks questions. So most of the questions used to come from biotechnology field. Okay, so if we go back to last 10 years question paper, most of the questions were from biotechnology. I mean more questions were from biotechnology. The next important area is space science and technology. All right. Third important area is information technology, defense technology. Then one or two questions comes, I mean on alternate years from nuclear science and technology. And this year nuclear science and technology is also very, very important. All right. Apart from this, when we talk about emerging technologies, from here also let's say questions come every year. Then from nanotechnology as well, questions come every year. All right. Then intellectual property rights, I mean on alternate years, maybe after 2 years gap, they do ask questions, one or two questions from intellectual property rights also. Okay, so these are the areas that are important for the UPSC prelims exam. Now when we talk about, let's say what is the nature of the questions that they ask in this science and technology section. So the nature of questions that they ask, it is very dynamic. Dynamic means they will take up the important concepts from science and technology and they will link it with current affairs. They are going to link it with emerging technology. Okay, so here the questions that they ask, these questions are mostly application based questions. I mean if they are asking a question, they will ask in which areas this particular technology is applicable. So application based questions are asked in the prelims exam. They generally take interdisciplinary approach, means they will try to connect multiple domains of science and technology within one question. Okay, I mean like multiple areas. For example, if they are talking about drone technology, they will try to connect it with biotechnology also. They're going to connect it with other agriculture as well. So that way we see interdisciplinary approach in the in the, let's say, prelims exam. Apart from this, let's say some of the questions have current focus also. Current focus means they do focus on the current affairs also, because science and technology is an emerging field. It's a field which is always, let's say like, emerging, growing. Nowadays we see artificial intelligence, right? A lot of GPUs are being created. Different types of artificial intelligence is coming. Apart from this, quantum science and technology is also emerging, quantum technology, right? Quantum communication, etc. So like we need to focus on emerging technologies also. However, we need to have a strong focus. Okay, we need to have a strong focus on which area? We need to have a strong focus on the let's say like fundamental topics. Okay, fundamental topics, that's the thing. Now so what are the sources that we need to focus? I mean like while we are preparing for science and technology, so we have written some primary sources, secondary sources and tertiary sources, all right? So primary sources means the NCERT books. So what you need to do whenever you are reading science and technology, you need to read, let's say like 11th and 12th NCERT, even 10th standard NCERTs are important. Few chapters are important and selective topics are important, because like science and technology, science, I mean like it's very in depth. If we go and start reading 11th standard science and tech, physics, so it will be very difficult. 12th standard is still more difficult. So these are the primary sources, like NCERT books are primary sources. NCERT books on biology, okay. There is class 11th NCERT biotechnology, class 12th NCERT biotechnology also.
Students, this primary sources look very confusing, sir. This NCERT part. When it says physics, chemistry,
see,
so
like, here what we have focused is we have given broader thing. I mean like we have not mentioned chapter wise. I mean like from 11th standard which chapter you need to read, from 12th standard which chapter you need to read. That we are going to do during the classes. I mean like when we are taking classes, so we are going to refer to those, I mean like chapters also. But like this is broadly we have mentioned that these standards NCERTs are important, okay. Because like today, in today's class also, when we talk about physics, I mean like physics, so we are going to touch upon 11th and 12th standard NCERT also, all right. So basically in primary sources, we need to understand that NCERTs are important, okay. NCERT books are important for the primary sources. When we talk about the secondary sources, okay, when we talk about secondary sources, okay, so Lukmaan IAS here, let's say like we do take Lukmaan Bulletin, which is earlier it used to be editorial discussion. So there also we cover a lot of science and technology topics. And in DTRS discussion that we take in the evening, so like we cover many topics. And these are tertiary sources. Tertiary sources means, I mean like, the websites of various departments of the government of India, websites of NASA, websites of other, I mean like, the primary sources, those websites are important. Then, I mean like, the Hindu newspaper and Indian Express newspaper, whichever you follow, so those newspapers are also important, all right. So these are the, I mean like, these are basic references to like what we need to follow to cover the science and technology portion. Now, let's say if we talk about the nature of questions that UPSC asks in the prelims exam, before we start the discussion, we need to talk about nature of questions also, so that like you have set, let's say like mindset that like we need to prepare according to this standard, because UPSC questions are the basic references. Because if you go through UPSC question, you will get to know that what is the standard of questions that UPSC is framing. So when we talk about this particular question, okay, so this question is, let's say like a statement, like assertion reasoning type of question. They have given two statements, okay. So when we talk about this particular question, so we are not going to discuss the answers as of now. We will discuss the answers after we take the discussion, all right. So here it says, consider the following statements. Number one, giant stars. Giant stars means big size stars live much longer than dwarf stars. Second statement, compared to dwarf stars, giant stars have greater rate of nuclear reactions, all right. So two statements are given, and what we need to do, we need to identify which statement is right. If first statement is right and second statement is also right, then we need to understand whether second statement is correct explanation of the first statement or not. So that way, I mean like, such statement based questions are also asked by UPSC, and the answers will be in this format, A, B, C, D. So this is one of the type of question that UPSC asks in the prelims exam. Then when we talk, so this particular question is related to giant stars. So we will discuss about stars, we'll discuss about planets and all. Then we will understand, let's say like, how star formation happens. Then next, I mean like, next question. This question is related to black holes. So it says, recently scientists observed the merger of giant black holes billions of light years away from the Earth. Okay, what is the significance of this observation? Question is, scientists observed merger of black holes. I mean like one black hole is there, other black hole is there, they have come together, they have merged. So now they are asking that like what is the significance of this observation, that scientists have observed that black holes have merged, what is the significance? So to understand the significance, we need to know what is black hole, then we need to know what happens when black holes merge. Okay, so they have given, I mean like, multiple options, and we need to select which option is correct. So if we go through both these questions, one thing is very common is that they are testing your understanding of the subject. They're testing understanding of the subject, that like, merger of black holes, what will happen? Okay, it's not very factual. It's about they're checking the understanding. But why they have asked a question from black hole? It is because black holes might have been in news in 2019. Okay, this question was asked in 2019. This question was asked in 2024, like that. Okay, so the thing is here, the conceptual understanding is tested. One thing, conceptual understanding is tested. Next thing is, let's say once the conceptual understanding has been tested, now what they are going to do? Now basically, I mean like, they are going to ask questions from multiple areas in science and technology. I mean like, if there are 15 questions, all the 15 questions will be from different areas of science and technology. And each question may have, let's say like, interdisciplinary approach. This particular question is from, let's say, space science and technology, or you can call it astronomy, you can call it cosmology and all. Okay, so like that. So this is, I mean like, this is another type of question. This type of question is basically observational, okay, and application based topics. Okay, this question is from observational and application based topics. All right, so if we talk about this particular question, okay, so in this question we can see, like in the previous questions, A, B, C, D were the answers. But in this question, what they have given multiple statements, statement 1, statement 2, statement 3. Now they are saying how many of the above actions is the function of the accelerometer required. Okay, how many of the above actions is the function of the accelerometer required? So here they are asking about accelerometer. Okay, so they have given statements. Okay, now only one, only two, let's say all three, none, means like this is one type of question that they are asking. Okay, so basically after we cover the topics, we will also go into detail how to solve such questions. Okay, this is another question here. The, I mean like, nature of this question, framing wise, is similar to that one. But here they have asked about exact options like 1 and 2, 2 and 3, 1 and 3, 1, 2 and 3, like that. Okay, so it can be that way also, it can be this way also. Because like, this is a new innovation that UPSC has done. They, nowadays, they are also asking questions of this nature, only 1, only 2. Basically, this is more easy to solve. Okay, or it depends on you. If you are able to eliminate one option, then you will be able to arrive at answer directly in this question. Okay, so this is, I mean like, now they are asking, consider the following communication technologies. Closed circuit television means CCTV. Okay, CCTV. Radio frequency identification, which is RFID. Okay, then wireless local area network. Radio frequency identification means if you have a metro card. Okay, I mean like, you go there, so okay, FASTag is also there. Okay, so that is RFID is used. Okay, which of the above are considered short range devices or technologies? Okay, which of them are considered short range? Okay, so here what they are checking our observational analysis, they are checking our application, I mean like, they are checking our understanding of these things. All right, so so having understood this, now let us talk about one important area. Okay, one important area. So the first topic that we are going to discuss today, okay, is Big Bang theory. Okay, we are going to discuss about this particular topic quickly. So we need to understand that what is Big Bang theory, why we are reading about Big Bang theory. Okay, so the topic 1 is okay. So this is topic 1 for us, which is Big Bang theory. So now we need to understand what is Big Bang theory and why we are reading about Big Bang theory. All right. So what is Big Bang theory? Big Bang theory actually helps us to understand how and when the universe was formed. Okay, how and when universe was formed. So to explain that particular concept, we have multiple theories. One of the most accepted theory is Big Bang theory. It is widely accepted among scientific communities. Okay, so that's why we are reading about Big Bang theory. So it talks about that how the universe began, how universe formed, right? And when universe was formed. So this theory helps us address two questions. One is how the universe was formed, when the universe was formed. Okay, so now how the universe was formed. Okay, second is when the universe was formed. Okay, so these are two questions that this theory addresses. This theory actually answers these two questions. Okay, how the universe was formed. To understand about how the universe was formed, it formed after a Big Bang. Okay, it formed after a Big Bang. What do we mean by Big Bang? It means a big explosion. Okay, Big Bang means a big explosion. For example, like during Diwali, what we do, like we basically use firecrackers. The explosion happens on a very small level. Wherever terrorist activities happen, bombing happens. Okay, so that's explosion happens. So the universe was formed, according to this theory, the universe was formed after a big explosion. Okay, big explosion. So what exploded? Question arises from here is what exploded, right? And why it exploded? Okay, question is what exploded? Basically, like the universe was formed at around 13.8, right? 13.8 billion years ago. Okay, billion years ago means when the universe was formed, it is like 13.8 billion years ago. But the question is, how do we get to know that like it was formed 13.8 billion years ago? Like, is it a random number or it is a scientifically calculated number? So we will understand about that also. It is a scientifically calculated number. They have arrived at this number after doing scientific calculation. So we will understand about it. Okay, Big Bang happened. Now to understand about big explosion, okay, to understand about the big explosion or Big Bang. Big explosion or Big Bang that has happened is, we need to understand that long back, there was a singularity. Okay, there was a point which is singularity. So I'm just making it white, but it was dark. Okay, so this particular point is known as point of singularity. Let me point of singularity. These keywords will help you to understand about further concepts also related to science and technology. So this is a point of singularity. What do we mean by point of singularity? It is a very small sized, very high density. Okay, point of singularity means over here two characteristics are seen. One is very high density. Okay, very high density. Second important point is very high temperature. Very high density and very high temperature. So long back, right? Long back, there was no time, there was no universe. There were no human beings, there were no planets, there were nothing. Okay, nothing existed long back. But the thing is, at that point of time, there was a very small point of singularity. This is like, point of very small singularity. And this has very high density. High density means materials are so much tightly packed. Okay, highly tightly packed. And it had very high temperature. So all of a sudden, right, all of a sudden, there was an explosion of this particular singularity. And that event, okay, that event of explosion, okay, that event of explosion is known as Big Bang, okay. That event of explosion is known as Big Bang. So Big Bang happened, all of a sudden explosion happened. Okay, when it happened 13.8 billion years ago, we will understand that like why, how we came about that particular figure. Okay, so Big Bang happened 13.8 billion years ago. 13.8 billion years ago. So what happened after the Big Bang? Okay, so when the Big Bang happened, I mean like within a fraction of seconds, which is 10 raised to power minus 43 seconds. Okay, within a fraction of second, I mean like less than a second, at a very smaller time, right? After the Big Bang happened, some particle came into being. I mean like some of the things came into being. I mean like after explosion, things go here and there. So those things came into being. So it was initially very high temperature. So the thing is slowly and gradually after that explosion. So what happens? Once explosion happens, things go in all direction. I mean like they expand in all direction. I mean like it is going in that direction, this direction, things expand in all directions. So the materials started expanding in all directions, and at a very small point of time, this particular point of time, something happened. I mean like those things started solidifying, and slowly and gradually, I mean like over a period of 13.8 billion years, the universe formed into the shape that we see now. Okay, I mean like planets emerged, galaxies emerged. Okay, as of now galaxies emerged. Within those galaxies, right, we have solar systems also. Within solar systems we have planets, we have, let's say, moon also. So all of these things formed, I mean like slowly and gradually, and as these things started moving away and away from this particular point, okay, they started getting cooler and cooler. Cooler and cooler means the temperature started going down. But the thing is, after the explosion, things that they were moving away, they are still moving away. What is happening? Those things that were moving away from after the Big Bang, it is still moving away. So what will happen? Let's consider, I mean like for a point of time, let's consider that like over here, if I am making a small circle, if there was a let's say object over here, object means particle, anything, there was an object over here, there is an object over here. So now they seem to be closer, but after some time when they are moving away, I mean like when they are moving away like this, so as the time is going, as the time is passing, okay, with the passing time, things are getting away from one another, more away. Okay, explosion is, I mean like expansion is happening. Okay, this is known as cosmic inflation. There is a scientific term. This scientific term is known as cosmic inflation. Okay, cosmic inflation. I mean, like if we have a balloon, if we let's say like fill air into that balloon, so it gets inflated, it becomes bigger in size. So now the universe is becoming bigger in size, and cosmic inflation is happening. Okay, cosmic inflation. I mean, like the cosmos or the entire universe is getting bigger and bigger. So if we talk about today, like, is it true that like now the universe is expanding? Yes, the universe is expanding. And how do we get to know that the universe is expanding? To understand about that the universe is expanding, we have multiple, I mean, like scientific methods. Okay, scientific methods. For example, today we are going to discuss about Doppler's effect. And through Doppler's effect, we will understand about redshift. Okay, redshift and blue shift. Basically, when the things are moving away, right, they basically emit let's say like electromagnetic waves or wavelengths that are, let's say like reddish in nature. So that's why we call it redshift. Okay, so since universe is expanding, redshift is happening. Okay, so we will understand about that. So the thing is, now we understand that before the Big Bang there was no universe, there was no concept of time. Concept of time emerged right after the Big Bang happened. Okay, now the question is, how do we trace back that like it was 13.8 billion years ago? We understand it through a law which is known as Hubble's law. Today we will discuss about Hubble's law also. All right, so I will showcase a diagram to you. Okay, why diagram? I mean, like this is one of the simplest diagram that I have gotten. Okay, one of the simplest diagram. So in this particular diagram here, let's say like this diagram explains the Big Bang theory. Okay, so let's consider long back there was a very small point over here. Okay, a very small point over here which exploded. After the explosion of this particular thing, things started, I mean, like inflating. Inflating means becoming bigger. So it is showing in this particular funnel shape. Why? Because the thing is like after the explosion, things are, I mean, like moving away from one another. Okay, so it is in all directions basically. Okay, so with the increasing age of the universe, the size of the universe is getting bigger. Okay, it is getting bigger, and as we are moving away, I mean, like from this Big Bang event, things are also cooling down. Okay, things are also cooling down. So basically, so Big Bang happened, right? At this point of time, some changes happened in the universe where atoms and molecules started forming. I mean, like means like protons, electrons, neutrons, they started coming together, right? Then dark age was there. There was a time. Then 300 million years after, first stars appear. Okay, at this point of time, early galaxies appear, and formation of the solar system, which happened in 9 billion years ago. Okay, so formation of solar system. So solar system is part of a galaxy. Okay, so galaxy is a bigger unit. Within those galaxies, we can have multiple solar systems. Within those solar systems, we can have multiple planets. We can have multiple, let's say, moons also, which are known as natural satellite of the planet. Okay, so the thing is, Earth is a part of the solar system where sun is, let's say, we will discuss where the sun is located. Sun is located at one of the foci of the solar system. All right, so like we are part of a one solar system, but we are part of Milky Way galaxy. Which galaxy? Let's consider today, let's consider there are multiple galaxies. Okay, we don't know how many galaxies are there because we don't have those instruments that can help us identify that how many galaxies are there. I mean, like we have not yet developed those capacities. But what capacity we have developed? We have developed that, like we have our solar system. We have identified all planets in our solar system. We are now doing research to understand about the sun. What is there inside the sun? Okay, and like what kind of reactions happen on the sun. And for that purpose, from India, we have launched a mission which is known as Mars Orbiter Mission, Mangalyaan mission, right? 2014 we launched it. I think 2013 we planned. Okay, and so it's been more than 10 years now, Mars Orbiter mission. So that is also known as Mangalyaan. So that was successful, right? Through Mars Orbiter mission, we have gotten some more understanding about the sun. We have not gotten all understanding about the sun. We have gotten some understanding about the sun through the Mangalyaan mission. Okay. After then, very recently we have launched another mission to understand about the sun. What is the name of that mission? Aditya L1 mission. Okay, Aditya L1 mission. So we will discuss about that mission also in detail, right? So that's the thing. And so basically, like, scientists from different space agencies of the world, like we have NASA, National Aeronautics and Space Administration. This is the space agency of USA, right? We have ISRO, Indian Space Research Organization in India. For Russia, we have Roscosmos. For Japan, we have JAXA. Okay. For China, we have China National Space Agency, CNSA, something like that. Okay. So like we have various space agencies. Major, like, you know, big countries are spacefaring nations. There are very few spacefaring nations. If we talk about space activities, so India lies somewhere in the 3rd or 4th country in the world related to major space activities. For example, let's say we have launched Chandrayaan, right? So which is, let's say, a mission for moon mission, right? Chandrayaan mission, we had Mangalyaan mission, right? So, like, you know, we are planning multiple missions. We are the ones who are able to send satellites into the space, right? Other countries are also kind of getting help, taking help from ISRO, right? And we will discuss about how, I mean, like, you know, the space sector is regulated in India. So we have multiple bodies. One of the bodies known as Department of Space. Then we have Indian Space Research Organization. We have INSpace, Indian National Space Promotion and Authorization Center, right? And we have also another body. Okay, so, like, you know, Government of India came up with Indian Space Policy in 2023 also. Okay, now we have a space policy also. So we will discuss about that. So basically here we need to understand that Big Bang is the event that has happened, and after then, I mean, like, you know, like particles started forming, and slowly and gradually as the time is passing, right, modern galaxies are formed. Within those galaxies we have stars also. Star means the sun. Okay, a star means a body that can emit energy also. Okay, that can emit energy. So this is the thing. So here if we talk about this particular thing, the time period that I have talked about, 10 raised to power minus 43 second, means 1 upon 10 raised to power 43 seconds, very small amount of time. So this particular time is known as Planck era, earliest meaningful time. Space and time take shape. Okay, space and time started taking shape at that point of time, which is 10 raised to power minus 43 seconds. After then, now it is considered there was no previous era. Matter, energy, space and time began abruptly with the bang.
What era will you say? The Planck era?
I mean, like, this particular time period is known as Planck era. Okay.
Planck or Planck, sir? Planck.
Planck, I mean, like, you know, it's a name of a scientist. Okay.
Okay, sir. Planck.
Like, name of a scientist. I mean, like, we may pronounce differently. He may pronounce differently. I may pronounce. Okay. Whatever I am pronouncing is to the best of my knowledge. Okay, that's the thing. I mean, like, it may not be the perfect ones, but to the best of my knowledge, I'm doing it. So this is the thing, Planck era. Now the question is, you don't need to correlate this Planck era with the geological time scale. You might be knowing about geological time scale, where we have epoch, we have eon, we have era, we have, let's say, like, you know, like various kind of time period, like, you know, how do we calculate time. So that geological time scale is according to when the earth was formed. Earth means the planet on which we are living, when it was formed, and after then what major incidents or activities happened in the planet, on planet earth. I mean, like, you know, like evolution of dinosaurs, right? And then there have been multiple phases of mass extinction, where life forms have gone extinct and again life forms have emerged, right? So there have been multiple cycles of it. Now when we talk about now this particular era, I mean, like, there were scientists who have proposed that we are in Anthropocene epoch. Okay, they have said, like, we are in Anthropocene epoch. Why? Because now human beings are let's say, like, you know, altering the, like, you know, nature of earth by their activities. I mean, like, you know, Anthropocene epoch. So they have proposed this particular thing. Okay, so here this particular time period is Planck era. It is earliest meaningful time. Space and time take shape from here. Okay, and so, I mean, like, before this Big Bang, it is considered no matter existed, no energy existed, no space existed, no time existed, like that. Okay, so this is a relative understanding. I mean, like, before this we do not have any understanding as of now. Okay, there can be multiple things that as human beings we can think about. Maybe in future, right, some more refinement to this particular theory may happen, or alternate theories may also be proposed by people, right, how the universe began, like that. And there can be multiple possibilities, but it is a matter of research and development. For example, we had multiple revolutionary scientists, I mean, like in the past. If we talk about Albert Einstein, we have all heard about him. Today we are going to understand about, let's say, theories of relativity of Albert Einstein also. Okay, we'll understand about that. Then quantum emergence. Okay, ordinary space and time develop out of a primeval state described by a quantum theory of gravity. Okay, so a quantum theory of gravity also exists. Okay, so that we will discuss in a later part. Okay, so if we talk about, if we have to understand about this singularity, singularity means, I told, there was a very small mass with very high density and very high temperature. So that singularity is very less explained by scientists as of now. Okay, so people say, like, we need to further refine the quantum theory of gravity to explain about that singularity also. Okay, so that's the thing. And multiverse, our universe and other bud off from eternal space. I mean, like, there is a concept of multiverse also. Multiverse means we understand that this is the universe, this is all, but there are other hypotheses also, other theories also that say parallelly there can be multiple universe that is existing simultaneously. So that is known as multiverse. That theory is known as multiverse theory. And there is another theory that is known as cyclic universe. Okay, cyclic, I mean, like, these are different types of, I mean, like, theories. Main thing is Big Bang theory. Okay, the theory that we are understanding, because this theory is backed by multiple demonstrations, multiple, I mean, like, observation by different scientists. Okay, many scientists have explained about this particular thing. Okay, so there was a person, his name is George Lemaitre. Okay, in 1927 he suggested that the universe is expanding from primordial atom. So George Lemaitre is a person, so he was kind of bishop in a church, kind of, I mean, like, we can say, like in church he was considered father. So he had that, I mean, like, two things. One is he has religious view also, then he was a physicist also. So he has said that, like, the universe is expanding, and, like, it started from a primordial atom, I mean, like, primary atom. Then Hubble, Edwin Hubble, in 1929, he talked about redshift in distant galaxies. So today we are going to understand about redshift, we'll understand about blue shift, we'll understand about let's say, like, Doppler's effect also. So these things. Okay, so this is about Big Bang theory. So after understanding about Big Bang theory, okay, so like we have already given the printed notes to all of you. Here in the classroom we are going to understand about these things, and you can read the topics, and later on we will solve questions on these topics. All right, so this is the thing. So having understood this, now let us talk about another, I mean, like, so any questions from this topic, Big Bang theory, anything that you feel that it is not understood? What is the
Big Bang होने के लिए जो basic reason क्या थी, क्या कारण था explosion होने के लिए?
एक्सप्लोजन होने के लिए बहुत ज़्यादा टेम्परेचर था, बहुत ज़्यादा डेंसिटी थी, तो it could not withstand that thing, so Big Bang happened. They said this thing. Okay, so I mean, like, they have explained the thing from an event, but how that event, I mean, like, what were the situations that led to that event, it is yet not explained. Okay, I mean, like, by scientists. So this is the thing. But the thing is, like, there are many things, many scientific theories, scientific experiments that prove that, like, whatever is explained over here after that is correct. So today we will understand about it. Yes. Any questions that you think, like, you have doubt about this topic, Big Bang theory? Yes. No doubt? Okay. So all of you can participate in the discussion. All right. So after understanding about Big Bang theory, so now we are going to talk about another topic, and this topic is known as Hubble's law. Okay. We'll discuss about that. Hubble's law. Okay, so this is, I mean, like connected with that topic, so that's why I'm taking it first. Okay, I mean, like after that. So what is Hubble's law? So Hubble was a scientist. I mean, like you might have heard about Hubble Space Telescope and all. So basically, he was a scientist who was doing studies on cosmology, right? He was doing a study related to astronomy and all. Okay, so he talked about recessional velocity. Okay, so there is a concept, okay, which is known as recessional velocity. So now let us talk about Hubble's law. Hubble's law. So what Hubble has said, Hubble has talked about a very important concept which is known as recessional velocity. Okay, recessional velocity. So what do we mean by this concept, recessional velocity? Basically, this is connected with the Big Bang theory that we have discussed. Okay, in Big Bang theory, what has happened? Initially, there was a singularity, and Big Bang has happened after this singularity. Big Bang has happened after this singularity. Okay, I mean, like things started going in all direction. So since things started going in all direction, now what is happening? I mean, like one object has, let's say, come over here, other object has come over here. Now, if we see from this particular analogy, right? So as the time is passing, things are moving away from one another. Things are moving away from one another. And what Hubble has observed that, let's say, like, you know, there can be one planet over here, there can be another planet. It can be any celestial body. It can be a planet, it can be a star, it can be a solar system, or it can be a galaxy. So what is happening? I mean, like Hubble has studied with reference to the Earth, with reference to planet Earth. So what he has done, he is saying that let's consider there is an object 1, there is an object 2, and there is an object 3. Okay, let's say this is an object 3. Object means a celestial body. Maybe anything in the universe. It can be a planet, it can be a solar system, it can be a galaxy also. So now all the things are moving away from one another. We know. I mean, like, you know, things are moving away from one another in the universe. I mean, like the universe is like, this is known as cosmic inflation is happening, right? So things are moving away. Now since things are moving away, I mean, like, you know, this object and this object, they are moving away like that. Okay, moving away. These two objects are also moving away from one another like that. Okay, but the thing is, an object which is located far away, an object which is so we are taking this particular object as reference. Okay, it is as reference. An object which is located far away is moving at a faster speed as compared to an object which is located nearby. Means like it is moving away, but they are not moving away with the same speed. This one is moving away with greater speed. This one is moving away with lesser speed. Let's consider there is another object. Let's consider this object is over here. Then this particular object is moving away from this particular object at a speed which is higher than the speed of this thing. And he called it recessional velocity. Recessional means going away from one another. Recessional velocity. Okay. So Hubble has given a law, and this law is explained by this particular equation. What equation? V equal to, okay, V equal to H naught D. V equals to H naught D. Okay, H naught. I mean, like, this is a notation. So this is considered to be Hubble's constant. Okay, Hubble's constant, and this is recessional velocity. Recessional velocity, and this is distance between the two objects under consideration. Okay, means if we have to remove this proportionality constant, so we will get to know that recessional velocity is directly proportional to the distance. Means if an object is located at a higher distance means far away, it will be moving at higher speed away from the body. Are we understanding? So this is known as Hubble's law. So now if we talk about this particular graph, okay, so on this graph the slope of the line is equal to Hubble's constant. This is the slope of the line. Slope means how much angle it is making, right, with x-axis. Let's consider this is x-axis, this is y-axis. How much angle it is making, that is known as slope of the line. Okay, it is known as slope of the line. Okay, so now over here what is happening, I mean, like, you know, in this particular graph, as the distance is increasing, right, recessional velocity is also increasing, right, as the distance of the particular galaxy, planet or anything from the earth is increasing, so its velocity is also increasing. So they have plotted like this, okay, for multiple objects in the universe. It may be planets, it may be that thing. So after plotting this particular thing, Hubble has given this law. So Hubble's law also explains that the universe is expanding. Universe is expanding means, like, you know, it is becoming bigger and bigger. Why? Because objects are moving away from one another. Are we understanding? So this is known as Hubble's law. Is it understood? So Hubble's law actually is helpful to explain the Big Bang theory also. So it basically supports the Big Bang theory. It supports the idea that the universe is expanding. Okay. It talks about the cosmological principle also. Okay. That the universe is homogeneous and isotropic on a large scale. Okay. Means the universe, I mean, like, as we see today.
What's isotropic?
So basically, like, it's a scientific concept. It talks about uniformity. Okay, so universe is uniform. I mean, like, matter in the universe is same. Okay, it's like that. So, like, we will just broadly understand about this particular thing. Okay, so basically Hubble's law supports the idea that the universe is expanding. It also supports the idea that Big Bang might have happened. Okay, because why? Things will always be moving away. If we just plot it backwards means, let's consider things are moving away. If we plot it backwards, what will happen? I mean, like, if we reverse it, imaginary, I mean, like, you know, if we imagine that now things are going in reverse direction. As of now, things are moving like that. If we imagine that things were coming, I mean, like, you know, closer. So we will come to that particular conclusion that once upon a time, there might have been a singularity. There might have been a point from where all these objects have emerged. Okay. Are we understanding this particular thing?
So when we say Hubble's constant, what do we mean by constant, sir?
Basically, like, if we talk about these equations, okay, is basically over here, Hubble, while he was doing the study, right, Hubble has come to know that the velocity of objects is increasing as the objects are moving away. But he wanted to make it an equation. So there must be some value. Okay, there must be some value. If we put that value, so this particular equation can be equated, and that value is known as Hubble's constant. Okay, that value. So we have given this value over here. Okay, so that value is known as Hubble's constant. Basically, like, we have studied these concepts in our maybe 9th, 10th standard mathematics classes also. Proportionality constant. Okay, I mean, law of gravitation and all. So basically, this is that thing, Hubble's constant. It's a kind of value. Okay, it is around. So it ranges from 68 to 74 kilometer per second per MPC, like that. Okay, so it's like that. Okay, so it varies. I mean, like, because some object is here, some object is here, it varies from value 68 to 74, okay, kilometer per second per MPC, like that. So it's a kind of equation. I mean, lot of technicalities are there, but here we are understanding the broader concepts only. Okay, we are not going into equations and all. So is it understood the Hubble's law? Have we been able to connect it with Big Bang theory? Okay, all right. So now let us talk about another topic. Okay, so we will quickly move from this topic to another topic. Yes, any question? No. Here, now we need to understand it is related to the space. I mean, it is related to space. I mean, like, like how the objects are moving away from one another. I mean, like you are talking about the speed, velocity, time with reference to that. That is speed, velocity and time that applies to the objects that are on the earth when we talk about Newtonian physics. When we talk about Newtonian physics, but here we are talking about the cosmology. Here, I mean, like, here we are not talking about, I mean, like we are not relating it with I mean, like, that way. So it is like velocity is proportional to distance. I mean, like between planets, between cosmological bodies. We'll discuss about that also. Okay, so slowly and gradually we'll be able to connect with the things. Okay. So basically, like his point is right. I mean, like speed, time, like that. So that way. So having understood that, now let us talk about another topic, which is Doppler's effect. Okay, Doppler's effect. Now, what do we mean by Doppler's effect? Okay, another topic, which is Doppler's effect. Now, what do we mean by Doppler's effect? Basically, this is related to perceived value of frequency, perceived value of wavelength. For example, let's consider there is an observer. Okay, I'll draw the diagram over here. Let's consider there is an observer standing over here. Okay, and maybe an ambulance is coming towards him. Okay, this particular object is coming towards him, maybe. It is coming towards him. So what happens, I mean, like you might have heard that whenever ambulance is coming towards you, right, it always keeps on, I mean, like, ringing its siren. I mean, like, it keeps on making that noise, siren, bajta rehta hai. So what will happen? When the ambulance is coming towards us, when it is coming near to us, the sound that we hear, it becomes steeper. I mean, like, zyada pitch, like its pitch increases. I mean, like, so there is a concept related to sound which is known as pitch. Okay, so pitch of the sound that we hear, right, from an ambulance which is arriving towards us, which is coming towards us, it increases. So, but the thing is, the ambulance might be making the same amount of noise, I mean, like same amount of sound when it was here, when it was here, when it was here. I mean, like it is playing the same thing, I mean, like same speaker, same thing, it is making the same noise. But when the sound is when the source of the sound is approaching towards us, we hear higher pitch, right? We hear higher pitch. So this is known as Doppler's effect. What we call this particular phenomena, we call it as Doppler's effect. Doppler is the name of a scientist. Okay, Doppler's effect. So what is Doppler's effect? Basically, Doppler's effect helps us to explain that the perceived value of frequency, right, of an object which is emitting sound or emitting light, right, perceived value of frequency changes, right, if the object is moving towards us or it is moving away from us. When we talk about this ambulance which is moving towards us, let's say like it is ambulance which is moving towards us, so perceived value of frequency increases. What happens? The value of frequency, let's say I am saying this is frequency, so that perceived value of frequency increases when it approaches towards us. But what will happen when the ambulance, let's say, passes through us and then let's consider it goes away? Then slowly and gradually that perceived value of frequency reduces for the observer, for the person who is hearing the sound. Okay, so like when it is approaching, the frequency increases, pitch increases. When it goes away, pitch decreases. Okay, similarly it happens with reference to light also, source of light. Now what can happen? Let's consider this ambulance can be stand still, means like it can be static. It is here standing, it is not moving, but it is making that constant noise that it was making earlier. Now it is making the noise and we are now coming towards the ambulance. Maybe we are on a bike, ambulance is making sound. we are approaching towards the ambulance, then also the perceived value of frequency will go up. Okay, either the source of the sound is coming towards us or we are going towards the sound. Okay, perceived value of frequency will increase, right? The perceived value of frequency will decrease when either of them, I mean like either the source of the sound or the observer or the hearer, right, moves away from the source of the sound. Either this particular source of the sound is moving away or the hearer, this particular person is moving away. Then also the pitch will go down like that. This phenomena is known as Doppler's effect. Okay, so we will understand about Doppler effect through equations also. I mean like, so we will understand some scientific terms associated with it. So now here we can consider two examples. In one example, the observer is located here. In another example, observer is located here. Now what is happening? This is an ambulance. It is source of noise. When it is coming towards us, you can see these, I mean like, we can say like these frequency things, right? They are closer, very close to one another. Means like pitch is increasing. I mean like when we talk about noise signals. So in case of noise signals, when they are very close to one another, it means like pitch is high. When they are away from one another, it means pitch is low. Pitch is low means like, consecutive frequency. I mean like frequency is higher over here. So here, higher frequency, higher pitch when the ambulance is moving towards us. Now, if we are standing over here and the ambulance is moving away from us, so the perceived value of frequency will be low, lower frequency, lower pitch, okay? When higher frequency, higher pitch is there, so like, we basically, like we talk about, we say it in terms of light blue shift, lower frequency means red shift, okay? So we will see it with reference to light also. With reference to sound, I hope you have understood, okay? Now this is the equation that helps us to understand about Doppler's effect, okay? What is the equation? It talks about F naught is equal to V plus V naught upon V minus Vs into F. So this is the original frequency. I mean like whatever noise that the ambulance is actually making, that is the original frequency, and this is the observed frequency. Observed frequency is equal to actual velocity of the sound waves plus V naught, which is V naught is equal to velocity of the observer. Okay, I mean okay. V naught is velocity of the observer upon V minus Vs, velocity of the source, like that, okay? So that way, okay, so this is the equation that helps us to calculate this value, okay? So with this, now let us talk about another scenario, okay? Here we will try to understand about red shift and blue shift, okay? Wherever the frequency, perceived frequency, okay, perceived means observed frequency, is increasing, we will say blue shift, okay. Whenever the perceived frequency is going down, reducing, we will say it red shift. I mean like the universe is expanding. Expanding means like objects are moving away from one another. What shift? Moving away, away. जब दूर जा रहे हैं, red shift. हाँ, दूर जा रहे हैं तो red shift. ठीक है, like that. So the Doppler effect is the shift in the frequency of a wave in relation to an observer due to the relative motion of the wave source and the observer. Okay, so this is the thing. Now, so this is about Doppler shift in sound. We have already understood about it.
So red is far away, sir. Red shift is so far away and blue shift is near objects.
Yes, when the things are going away from one another, red shift happens. Okay, when they are coming towards one another, so I mean like blue shift happens.
Okay, sir.
Same thing, I mean like same thing we discussed.
Yes, sir.
Okay, so this is another example of Doppler shift in sound. Okay, so this is source, this is observer. I mean like when none of them are moving, so like he hears the same frequency. I mean like it is like that. If the source is here, I mean like moving towards the observer, I mean like let's consider this is the observer, so higher frequency will be here, lower frequency will be here. Again, if this particular thing, so this is the example of a train, if it is moving towards this particular observer, so here pitch will increase, frequency will increase, here frequency will decrease like that. Okay, so this is the thing. Now this is related to galaxies. So we have already discussed that the universe is expanding. Universe is expanding. So related to that, what is happening? Like this is an observer. Okay. So when galaxy is receding, receding means like when objects are moving away from one another, we will see redshift. So in the universe in general we see redshift. Okay, we see redshift. It is like that. Okay. But the thing is, like if we talk about light sources, we discussed about sound sources, but in the universe light sources also, I mean like there can be a light which is approaching towards us. Maybe let's say like we are receiving light from a distant galaxy. When it is approaching towards us, so like its frequency will keep on continuously increasing slowly and gradually, some light which is coming towards us, slowly and gradually it is coming. So its frequency will slowly and gradually keep on increasing like that. Okay, so that's why I mean like you might have heard about, let's say newspaper, that scientists from NASA, they have discovered light from a distant galaxy or distant planet, and this has helped them to identify that an exoplanet exists like that. Okay, because they are located billions of light years away from us. Okay, light year is a concept from where UPSC has already asked questions. Okay, so when light waves squashed blue shift. Okay, squashed means when they come together. Okay, when light waves, I mean stretched. Okay, so it is redshift simply. So this is Doppler's effect. I hope you have understood about Doppler's effect. Any question related to Doppler's effect? Okay. So from here, we'll quick.
So you said that light from far away from towards us, frequency and light increase. What is that, sir?
Basically, let me give you an example. Okay. Basically, after this, we are going to discuss a topic which is Einstein's theory of relativity. In that theory, basically, in the general theory of relativity, Einstein said that gravitational waves exist. What? Gravitational waves exist. It's a kind of new concept. Okay. But the thing is, like, he has said this particular thing in 1915. We are in 2025. I mean, like 110 years away. Okay, from that. He said that particular thing, that gravitational waves exist, but we did not have any instrument to measure that gravitational wave actually exists. What is this? Okay. He said, what is this? What is gravitational wave? Basically, today in the beginning, we have discussed a question number 2, which was there on the right side, that talked about the two black holes came together. They have merged, right? So when two black holes merged, what has happened? When black holes merge with one another, they create ripple in the space-time fabric. We'll discuss what do we mean by space-time fabric. We can consider that if two objects come together, they collide, so some kind of rippling effect happens, vibration happens. So there, when the black holes merge, that vibration is created, and that vibration emerges, right? It kind of emits gravitational waves. Okay. Albert Einstein had postulated that. He said that gravitational waves exist, but these waves are very weak in nature. Weak in the sense they come from very distant sources whenever black holes are merging or a black hole is collapsing. We'll discuss, like, I mean, like when a star collapses, it becomes a black hole. We'll discuss. So when it happens, it emits gravitational waves. And very recently in 2015, scientists from USA, they have created a detector which is known as LIGO detector. They have LIGO detector and Virgo detector. LIGO stands for Laser Interferometer Gravitational Wave Observatory. Okay. Laser Interferometer Gravitational Wave Observatory. So it's a kind of instrument setup that helps us to identify that gravitational waves are there or not there. I mean, like whether they exist or not. So using those instruments, they have been able to identify that gravitational waves actually exist. And then these people who developed this system, I mean like LIGO detector, they have been awarded with Nobel Prize in physics. Okay, I mean like, maybe a year after that, maybe in 2016, they have been awarded Nobel Prize in physics. All right, this is the thing. So basically, her question is related to light sources. Okay, so can you repeat that question?
Sir, you said like if you receive light from far away, its frequency and the light kind of changes. What will change in hospital, sir? What does that effect really causes?
Okay, so let's consider there is an object which is very far away. Its light is coming towards us. I mean, like, since they are very far away, I mean, like, light also takes time to travel. What is the speed of light? The speed of light is 3 into 10 raised to power 8 meters per second. This is roughly equal to 3 lakh kilometer per second. Okay, 3 lakh kilometer per second. This is the speed of light with which lights move. There can be an object which is coming towards Earth. Let's say it is coming towards Earth or it is going away from the Earth. Its light is coming towards us. Let's say its light is coming towards us. When the light is coming towards us, so slowly and gradually one light means like some source of light will come. Maybe the intensity of light will keep on increasing. Okay, intensity of light keep on increasing. So if it keeps on increasing, then we will see a blue shift in that light. Perceived frequency will go up in the instrument from where.
Because it's coming near us, sir.
Yeah, because it's coming, I mean, like, its intensity is increasing. Okay, I mean, like, you know, like waves are very close to one another, like that. So we'll discuss about that also. Okay, it is that way. Okay, so I mean, like, huge number of discoveries keep on happening. There are endless things in the universe. Okay, so everything is not discovered and it is not possible for us to discover everything. We do have limitations, but like based on those things, okay, I mean, like, we keep on doing the thing. So I hope up to this everything is clear. Any question related to Doppler's effect? All right. Now we will discuss about another topic which is from space science and technology. It is Kepler's laws of planetary motion. Okay, Kepler's laws of planetary motion. So what do we mean by Kepler's laws of planetary motion? Okay, so basically we know in the universe we have multiple planets. So when we talk about planets, so we will take the reference of our solar system. In our solar system, we have the sun. Okay, we have the sun, and then near the sun, I mean, like, you know, some planets are very near to the sun. Okay, some planets are away, so they are kind of, you know, revolving around the sun. We see that thing, right? Some planets are revolving around the sun. But Kepler has explained, Kepler has told that how these planets, I mean, like, you know, move. So he has given certain laws of planetary motion. So today we are going to understand about how the planets move around the sun, okay, around the sun in our solar system, and also how the planets move around other suns, other stars in other solar systems, like that. Okay, so to understand this, let's move to this topic. Okay. Kepler's laws of planetary motion. Okay, so Kepler's first law of planetary motion. Basically, he has given 3 laws related to planetary motion, and we are going to discuss about the first law now. Okay, so we'll discuss about what did Kepler say about planetary motion. So in the first law, basically, what Kepler has said that we'll draw a diagram, then we will explain about it. Okay, so this is the diagram. So over here what Kepler has said, that the all planets revolve around the sun in an elliptical orbit. What kind of orbit? In an elliptical orbit, where sun is located at one of the foci. Okay, so this particular diagram, this shape, I mean, like, if I draw a diagram like this, you will say this is a circle, right? If I say what is this, you will say this is a square, maybe. If I say what is this, you will say this is a rectangle. If I say what is this, you will say a triangle, like that. So similarly, geometrically, this particular diagram is known as ellipse. What is the name of this diagram? It is known as ellipse. Alright, this diagram is known as ellipse. So in the first law of planetary motion, what Kepler has said that all planets revolve around the sun in an elliptical orbit. Okay, all planets revolve around the sun in an elliptical orbit. Let's consider this is a planet. Okay, so it is orbiting around the sun in this particular orbit, which is elliptical orbit, like that. Okay, so all planets revolve around the sun in an elliptical orbit. That's the thing. So this is first law of Kepler's first law. Now before we go ahead, we need to understand what is there in this ellipse. Okay, basically in this ellipse, this particular distance, I mean, like, let's consider this is the center or origin. So this particular distance is known as semi-major axis. This is again semi-major axis. These two together forms major axis. Okay, major axis. Major axis is equal to 2a. A plus a. A plus a is 2a. This distance from this extreme end to here, from here to this here. This is major axis. Its length is 2a. Then from here to here, let's say this is b. Okay. Again this is b. So this is, I mean, semi-minor axis. And so if I talk about what is minor axis is equal to b plus b is equal to 2b. Okay. So this ellipse has two focus. I mean, like, let's say this is focus 1, this is focus 2. So sun is located at one of the focus, which is, both of them are known as foci together. I mean, like, f1 comma f2 are foci. This is plural form, foci. So sun is located at one of the foci. Now the question is, ellipse can be of different types. Okay, ellipse can be of different types. I mean, like, this is an ellipse, this is an ellipse, this is an ellipse. Circle is also a special form of ellipse, and line is also a special form of ellipse. So that value is eccentricity. There is a term which is known as eccentricity. I mean, like, this is denoted by E. So what is eccentricity? Its value ranges from 0 to 1. Okay, its value ranges from 0 to 1. 1 means highly elliptical. Highly elliptical means it will form a line. I mean, like, if we have two kind of thread, I mean, like, let's say we have connected, and that thread can be made a circle, can be made like that. So highly elliptical means eccentricity 1. Very low elliptical means it will be circular. Okay, so that eccentricity value of E varies. So that's how, I mean, like, value of this shape also varies. Means, like, all planets are not moving in same, I mean, like, same shape. Some planet can be like this, some planet can be like this and all. It depends on the value of eccentricity. Okay, but what Kepler has said in his first law, that all planets move, okay, or revolve around the sun in an elliptical orbit. This is Kepler's first law. Is it understood? Kepler's first law. So Kepler said all planets revolve around the sun in an elliptical orbit. Okay, this is the first law. So now, having understood this, okay, this is the first law. All planets move around the sun in an elliptical orbit with sun at one of the foci. Sun is located at one of the foci. This is Kepler's first law. Okay. So this is major axis. I mean like this will be A, this distance will be A, this is B, this is B. Whole 2B will be minor axis, whole 2A will be major axis. Now the planet can be very near to the sun or it can be extremely away from the sun. When it is near to the sun, near, we use the word perihelion means sun, near to sun, perihelion, okay. Then away from the sun is aphelion, okay, away from the sun is aphelion, okay. So when the planets are moving, right, so they can move near the sun or they can be very away from the sun. Now what happens from the first law, what we can infer is that when the planets will be very near, they are going to experience more gravitational pull from the sun as compared to when the planets will be away from the sun. Okay, we know the so we know gravity, force of gravity, G m1 m2 upon r square. I mean like it is a separate formula, universal law of gravitation. I mean like, so this is m1 into m2 upon r square. I mean like, you know, two bodies when they are very near to one another, they are going to experience more gravitational pull towards one another than when they are away. Means when the planet, I mean like planet is near to the sun, it is going to experience more gravitational pull, right, as compared to when the planet will be away from the sun, okay. So there are 2 days, I mean like one is I think 5th of September and some days are there, okay. So when, I mean like, you know, we say that the now planet is very near to the sun, planet is very away from the sun, I mean with reference to earth, okay, 2 important dates are there. हाँ, इक्विनॉक्स से रिलेटेड है, मतलब these are concepts, okay. Geography में like when you open the chapter, so we'll get to know कि position of the earth with respect to sun, ठीक है. Now we have another law which is Kepler's second law. First law is understood by all. Kepler's first law, okay. Now Kepler's second law, let us discuss. It says a planet sweeps out equal areas in equal intervals of time. Okay, a planet sweeps out equal areas in equal intervals of time. Now, what do we mean by area? Let's consider this is the planet. The planet can be at position 1, at position 2. I mean like here position 1, position 2. If we connect this planet with the sun, I mean like a single line like this is a line. When it is here, a single line. So these 2 lines and this particular distance, they are making an area, okay. We are saying this is area 1, okay? This is area 1, distance 1, area 1, right? Then now what is happening when the planet is near to the sun, maybe this is point number 3 and point number 4, okay, from here to here. Again we can make an area like this. The second law says a planet sweeps out equal area in equal intervals of time. Means from here to here, if it has taken t1 and here to here it has taken same time, let's say like we are seeing about maybe 5 days, okay, let's say we are seeing 5 days. 5 days मतलब maybe let's say 24 hour के हिसाब से अगर हम देखें 24 hour, okay, let's say I mean like 24 hour में एक बार वो rotate भी कर लेता है completely. So 24 hours में, within 24 hours it is moving from here to here. Then same 24 hour can be, it is moving from here to here and all. So whatever area it covers in those 24 hours, it will be same, okay, like this. So from here, what we can infer that when the planet is away from the sun, it has lesser speed as compared to when the planet is near to the sun. When the planet comes near to the sun, its speed, right, its speed with reference to sun is very high. When it is away, its speed is low.
So please repeat that, sir.
Okay. Now, first thing is we need to understand what is second law. Second law, a planet sweeps out equal areas in equal intervals of time. To calculate areas, what we have done, we have connected 3 points. Let's say this is point S, P1, P2. Okay, S, P1, P2 gives us an area which is area 1. Okay, it is an area. Similarly, this will be another area, okay, which is S, P3, P4 is area 2. Okay, so this planet is sweeping out equal areas, it is covering equal area in equal intervals of time, means like 24 hours, 24 hours. The area that is there under this shaded region, this area is same. But if we see this diagram, from this diagram what we can infer is when the planet is located away from the sun, when the planet is located away from the sun, it moves slower, its speed is less. When the planet is away from the sun, okay. When the planet is near to the sun, its speed is higher, okay. And also when the planet is near to sun, it is going to experience more gravitational pull, okay. Which is basically, here we talk about angular momentum is conserved, basically angular momentum, conservation of angular momentum. But in simple language, we need to understand that a planet sweeps out equal areas at equal intervals of time, okay. This is the thing. And when the planet will be away, it's going to move slow. When the planet is near, move fast. And this point is known as perihelion. This is the nearest point that planet Earth can come to the Earth. This is the farthest point that the planet Earth can come to the Earth, like that, or any planet. I mean, like, you know, every planet is at a different orbit. So let's say this is the path that a planet follows around the sun is known as orbit. That path is known as orbit. So every planet is moving in a different orbit. It is a different orbit. And they are not on the same plane also. Yes, yes.
What is the reason for to take more speed and less speed, sir?
What is the reason for more speed and less speed?
Yes, sir. Yes, sir.
See, gravitational pull.
Okay, sir.
Basically gravitational pull. And so to conserve the angular momentum, it is moving faster. That's the thing. Okay. So this is the thing. Okay. So is it understood, the second law? So before we move to the next third law, I will ask what was the first law?
All planets revolve around the sun in
All
an
planets
elliptical
rotate around the sun in an elliptical orbit.
Right. Shri Naik is right. You are also right. All of you are right. All planets revolve around the sun in an elliptical orbit. Okay. So this was the first.
What is the application of second law, sir?
We'll discuss. Okay. So application of second law is that, let's say, like, you know, basically here we need to understand when planets are located closer to the sun, they are going to orbit at a faster speed. Let's say this is sun, a planet is near, they are going to orbit faster, so they will take lesser time to complete one revolution around the sun. Let's consider Earth is taking 365 days and 4 hours, 365 days to complete one revolution. A planet which is located near than Earth, near to sun, okay, it's going to take less than 365 days. A planet which is located away from the sun is going to take more time as compared to Earth. That's the thing. That's how we can understand. Okay.
Okay, sir.
Huh? Acha, eccentricity, it talks about what is the shape of the ellipse. I mean, like, an ellipse can be like this, extremely elliptical. It can be like this also. It can be like this. A circle is also an ellipse where eccentricity is equal to 0. Okay. I mean, like, eccentricity is a kind of mathematical term. Okay. So all ellipses are not same. Some may be highly elliptical, some may be lesser elliptical. Circular also, like that. Okay. So this is the thing. And then planets can move in different planes also. I mean, like, there can be a plane like this. Okay, this plane is different as compared to that plane. There can be a plane like this also. Okay. हाँ, ऐसे होता है. ठीक है, गोल गोल घूमता है, like we could not understand. So it is like that. So before we move to the next topic, tell me what is the second law? Second law of Kepler's second law.
Planets sweeps out equal areas in equal interval of time, sir.
Wow, right. She's right. A planet sweeps out equal areas in equal intervals of time. And the thing that we have discussed, then when it is near to the sun, it is going to move faster. It is inference from that law. Okay, like that. Now let us move to the third law. Okay, Kepler's third law of planetary motion. Alright, Kepler's third law of planetary motion. So what is this? It says the square of the orbital period of a planet. The square of the orbital period of a planet is proportional to the cube of the orbit semi-major axis. Okay. Now let us understand. What is the orbital period? What is the orbital period of Earth? So you will understand. It is 365 days. In general, 365 days, 4 hours, like that. So 365 days is the orbital period. Means the time taken by a planet to complete one revolution around the sun. That is orbital period. So orbital period is denoted by the letter T. So T for Earth is going to be 365 days, like that. Okay. Then T for other planet. For Mars it will be different. For Jupiter it will be different. For maybe, Neptune, Uranus, it will be different. So every planet has a different orbital period. Now major axis is 2a. What is semi-major axis? Semi-major axis is equal to a. So the third law says that there is a relation between how much time does a planet takes and how far away it is located from the sun. Okay, that relation is mathematically expressed like this, that T square is proportional to a cube. T square is proportional to a cube, means if the planet is located far away, right? If it is located far away or near, so it's going to have an impact on the orbital period of revolution, right? Orbital period, how much time does it take to complete one orbit around. See, this is an ellipse, this shape, and extreme ends, ये जो सबसे लंबा वाला end, these extreme ends, this is major axis, and these extreme ends, this is minor axis. This is one of the center kind of thing. Okay, so from here to one of the extreme ends, the far away is semi-major axis, this one. Okay, this is semi-major axis. This is semi-minor axis. This is semi-minor axis. Okay? So T square is proportional to a cube. So from here, what we can analyze is, if we know, if we know, let's say, orbital period of Earth, if we know the value of A of Earth, and if we know the value of A of any other planet, we can calculate the orbital period of that planet. We don't have to observe it throughout the year to see how much time it has taken. Using this relationship, we can calculate. Okay, so it's like that. So the square of the orbital period of a planet is proportional to the cube of the orbit's semi-major axis. This is, Kepler's third law of planetary motion. So Kepler has given 3 laws of planetary motion. Okay, so these 3 laws actually inspired Newton to come up with universal law of gravitation. Okay, basically, after Kepler, he has come up with this. Okay, universal law of gravitation. That every object in the universe attracts every other object with a force which is proportional to the product of their masses and inversely proportional to the square of the distance between them. That was inspired by this, basically. So Hubble's law we have already seen. Okay, Kepler's law we have seen. We have seen Doppler's effect also. Now we are going to move to another topic. Okay. Yes, we have also seen Big Bang theory. Now we will move to another very important topic, which is theories of relativity. Okay, so theories of relativity is again very important. Okay, today is just an introductory lecture. Okay, so more important topics we are going to cover. These topics are very fundamental, very important. If the basic knowledge is clear, then you will be able to solve questions by seeing it. You will be able to connect that, like, where this question is, what this question is asking. Okay. So this is topic number 6, let's say. Is it topic 6 or 5? 5. Theories of relativity. Okay, so these theories of relativity were given by Albert Einstein. Okay, so basically he has given 2 theories of relativity. The first theory is known as spatial theory of relativity. Spatial theory of relativity. And the second is known as general theory of relativity. Second is known as general theory of relativity. Okay. So, spatial theory of relativity was given by Albert Einstein in 1905. General theory of relativity was given by him in 1915. Means like after 10 years, after a decade. So it took him 10 years to come up with general theory of relativity. Now the question is, what is the difference between a spatial theory and general theory of relativity? What is theory of relativity, right? So we need to understand about all of it. Alright. So I would like you to write a quick line. Write down a line quickly, all of you. Okay. The theories of relativity, comma, formulated by Albert Einstein, in the early 20th century, fundamentally transformed, write it down, fundamentally transformed our understanding of space, time and gravity, full stop. Write down two interrelated theories of relativity are: number 1 is spatial theory of relativity in bracket 1905, and number 2 general theory of relativity in bracket 1915. Okay, have you written? Now we will talk about the first theory, which is spatial theory of relativity. Spatial theory of relativity. Now, here we need to understand, when we talk about a spatial theory of relativity, Albert Einstein has talked about frames of reference which are moving at uniform speeds with reference to one another. Okay, so he has talked about frames of reference that are inertial frames of reference. Okay, here he has talked about inertial frames of reference. Okay, he has talked about inertial frames of reference, or frames of reference that are moving at uniform speed with reference to one another, uniform velocity with reference to one another. Now let us talk about what do we mean by frame of reference. Okay, so over here what I have done, I have drawn a diagram of a person who is standing and a car which is approaching. Okay, over here this person is just standing. Okay, this person is just standing and this car is moving. Okay, car is moving. Okay, at uniform velocity. Okay, or uniform speed in a single line. So what is happening, this particular frame will be called as frame of reference. I mean, like, one observer is there, another object is there. This object is moving towards the observer. So here we need to understand, Albert Einstein has talked about special theory of relativity in the context of inertial frames of reference. I mean, like, these frames of reference are those frames of reference which is not accelerating. Okay, if a frame of reference is accelerating, it will be considered to be non-inertial frame of reference. Here the objects are moving at constant speed or uniform velocity with reference to one another. Okay, either both are moving or one is moving, other is stationary, like that. Okay, either both are coming towards one another, both are going away from one another, one of them is at rest and other is moving towards it or away from it, like that. So this is inertial frame of reference. But to give the special theory of relativity, Albert Einstein has taken two things for as, I mean, like, if these two things are considered, if these two things are true, in that case his special theory of relativity will be valid. What are those two things? Number one thing that he has talked about, these are two hypotheses, or we can say, like, he has taken two postulates. Okay, he has taken two postulates. So what are those two postulates? Number one, okay, number one is, write down. Okay, over here write down. I mean, like, why it is important for you to write down, so that, like, you can understand these technical terms. I mean, like, some of you may be non-engineers, some of you may be, I mean, like, have not studied physics, I mean, like, you know, to that level. So write down the special theory of relativity. The special theory of relativity. Huh? So she does not have this thing. Huh? The special theory of relativity was published in 1905. Was published in 1905 and addresses the physics of objects. And addresses the physics of objects moving at constant speeds. Moving at constant speeds, comma, particularly those that are approaching the speed of light, What is the speed of light? Speed of light is denoted by the letter c. It is equal to 3 into 10 raised to power 8 meters per second. Okay, 3 into 10 raised to power 8 meters per second. This is the thing. Now here we need to understand that c is equal to this. Now Albert Einstein has talked about those objects that are going to move at a speed which is very near, very close to the speed of light. I mean, like, very fast moving objects, right, in the universe basically. So he has taken two postulates. Now it is grounded in two key postulates. Number one, it is grounded in two key postulates. Number one, the laws of physics are same for all observers in uniform motion related to one another. the laws of motion are same for all observers moving or which are moving at uniform speeds or uniform velocity relative to one another. What does this postulate mean? Okay, basically to understand this postulate you need to have understanding about let's say Newtonian physics. Like Newton has given laws of physics. I mean, like, you know, Newton has given 3 laws of physics. So those are known as classical laws of physics. For example, an object tends to remain in its state of rest or of uniform motion until it is, let's say, like, you know, pushed by, or let's say, like, you know, by some external force. That is first law, like Newton's first law of motion. Okay, this is also known as law of inertia, right? Second law of motion was F is equal to mass into acceleration. Okay, so that is also known as law of momentum, basically. Second, okay, rate of change of momentum is equal to acceleration, like that. And third law is, to every action there is an equal and opposite reaction. I mean, like, these were 3 laws which were given by Newton. So over here Albert Einstein is considering that the laws of physics are same for all observers if they are moving in uniform motion with respect to one another. Let's say I am at rest, you are moving in uniform motion. So with respect to me you are moving, or with respect to you I may be moving, because you are moving, I am at rest, with respect to you I may be moving. So he is considering that laws of physics will be same. I mean, like, these laws of physics will not vary with one another. This is first postulate, means like he has considered that this is going to be true. All right. Then second, okay, he has talked about another postulate also. He is going to take 2 things for granted. I mean, like, he is going to take that these 2 things are true. And based on this, he has given the special theory of relativity. What is the second thing? The speed of light in vacuum is constant and independent of the motion of light source or observer. Okay. So he said that the speed of light in vacuum is constant. Speed of light in vacuum is constant, irrespective. Constant means c is equal to 3 into 10 raised to power 8 meter per second. Means like speed of light will be this much value. Okay, irrespective of the motion of the source of light or observer. Okay, irrespective of the motion of source of light or observer. So what he said, these 2 things he considered that these are going to be true, and basis on this he is going to give the special theory of relativity. First thing is, laws of motion are same for all observers in a uniform motion, I mean, like, which are there in like, you know, inertial frames of reference. Second is, the speed of light is going to be same in vacuum. Vacuum means outer space where no, I mean, like, you know, where no medium is there. Okay, like that. So based on this, what he said, he talked about, okay, he talked about the special theory of relativity. So he discussed about many things. What he discussed, basically we are going to discuss. One, he said time dilation happens. What do we mean by time dilation? We'll understand. Okay. So he talked about many things. Number one is time dilation. So to understand time dilation, we need to understand about, there is a paradox which is known as twin paradox. There is a paradox which is known as twin paradox. What do we mean by this? Let's consider two brothers are there. They are on the, they are twins. One brother is here, other brother is here. They both are of the same age. They look the same. Okay. This is twin brother 1, twin brother 2, like that. Okay. So what they are doing, they are on Earth. Now they have decided, one of them has decided that like I'm going to be kind of, I'm going to go on a spacecraft. I don't know how to make a spacecraft. Okay, let's say. Okay. One of the brother decides that he is going to go on a spacecraft and he is going to go on a voyage. Voyage means like, Captain Vyom. अंतरिक्ष में घूमेंगे, ठीक है, he decided. So one of the brother goes on this spacecraft and then he spends, few years in outer space and all, then he returns. Let's say now their age, before they left, each of their age is 25 years. 25 years. Let's say he returns after 35 years. Okay, after 35 years with reference to Earth. So plus 35 will be there. So his age on Earth is going to be 80 years. But this person was on the move. He was moving on a space shift. Then he came back. When he came back, he found that this particular brother looks much older. Who was on Earth, वो बहुत बूढ़े हो गए हैं. He became very old and he was still much younger. The one who came from the outer space and all. Huh? Okay. Interstellar. Okay. Okay. So he came back. Now when he came back, he met with his brother and he found his brother has become very old and he is not old. So what we can infer from here is that a person who was on the move, his clock was running slower. A moving clock runs slower as compared to a clock which is stationary. A clock at stationary runs faster. So this is, this is known as time dilation. Okay. So if a clock is there which is moving, so it's going to move slower. Clock is going to tick slower as compared to a clock which is stand still. So it is a counterintuitive effect of special theory of relativity. Okay. So this is the thing. Okay. So this is known as time dilation. This is just an example. And however, this has been actually experimentally done also. If you search on the Google twin paradox, okay, you will come across those brothers, one of whom stayed in outer space. Recently, some people went and they came after 9 months, so they have been in news. Maybe you may expect a question in the prelims exam related to some of these things. They may connect with one of these things like that. Okay. So time dilation, is it understood? So what does time dilation says? Write down time dilation keyword, because these concepts are very interrelated with one another. If you don't write down, maybe you may not be able to retain the facts also, although it is written in the notebook. Okay, write down. Time is experienced differently. Time is experienced differently. We are writing about time dilation. Okay, time is experienced differently for observers in relative motion. For observers in relative motion. Full stop. A moving clock ticks slower compared to a stationary clock. From the perspective of an observer, I am repeating the line, a moving clock ticks slower compared to a stationary clock from the perspective of an observer at rest. Okay, so this is known as time dilation. Okay, is it understood time dilation concept? A clock which is moving is going to tick slowly as compared to a clock which is stationary, with reference to an observer which is at rest, which is stationary. Okay, so an observer is at rest, the clock is at rest, so this clock is going to tick faster as compared to the clock which is on the move. Okay, it's like that. So that's why satellites that are there, I mean like their clocks are adjusted from time to time. Okay, very small amount of adjustments are done, okay, from time to time. So this is time dilation. Having understood the time dilation, now let us talk about another topic in the sense like another counterintuitive effect of a special theory of relativity. This is known as length contraction. Length contraction. And this year, this topic is very important. Sunita Williams, I mean like, you know, people who stayed in space station, I mean like, you know, some of these things may be related. Then, I mean like, we will understand both the theories of relativity. Then if a question comes, you will be able to answer those questions because you have clarity of the concept. Now, length contraction. What do we mean by length contraction? Here, length contraction is a perceived thing. Okay, it is a perceived thing. It means, let's consider an object which is moving. Okay, an object which is moving at very high speed closer to the speed of light. That object is going to be seem, I mean like it's going to look smaller as compared to an object which is at rest. Okay, let's say I am an observer, an object is moving towards me at very high speed. Okay, that object is going to look smaller to me as compared to an object which is not moving, stationary object. This is known as length contraction. I mean like, you know, while moving, its length appears smaller. Okay, so write down length contraction. Okay, under this write down a sentence, length contraction. Objects moving at high speeds, objects moving at high speeds appear shorter in the direction of motion, when observed from a stationary frame. Okay, so is the length contraction understood? This length contraction thing has also been experimentally seen. Okay, so you might have heard about this particular thing, CERN.
Yes.
Have you heard about this? Yes. Have you heard about this term, CERN?
In France.
Yes. What is this? This is an organization where they, I mean like, you know, they have large hadron collider, a kind of, you know, they have a large setup to accelerate the particles at a very high speed, I mean like close to the speed of light. And then they observe the kind of, you know, properties of different types of particles after accelerating them. Okay, so this is the thing. So CERN, I mean like some European, like, you know, European organization for nuclear research, kind of that thing. Okay, Council for Nuclear Research. So basically it is written in France, so that way it is. Okay, so over here, I mean like here they have done, they have identified hadron. There is a God particle also, you might have heard about it, Higgs boson. They have identified that also. They have identified many subatomic particles over here. Yes?
Higgs boson particle, what is it exactly?
Okay, Higgs boson particle is also known as God particle. So what is God particle? I mean like, you know, to the scientist who has identified Higgs boson, he has been awarded with Nobel Prize also in physics. So Higgs boson is a particle, I mean like when it interacts with other particles, okay. So Higgs boson and Higgs field, these are two interrelated concepts. So when they interact with other particles, they impart mass on them, they give mass to them, okay. I mean like, so there is a field, Higgs field, okay. When it interacts with some particle, it imparts mass to them. So the particle that interacts with it, it gets mass. So all the objects in the universe, I mean like, that we can see, right? So they have interacted with the Higgs boson, okay. Higgs boson is abundant, okay, but like it is short lived, okay. So they are formed, they are kind of destroyed, okay, within, I mean like very small amount of time. So Higgs boson is the particle which interacts with other particles, right? It gives mass to them, that is the thing. And there is one particle which does not interact, I mean like some particles interact, some particles do not interact. The particles that interact, they get mass. The particles that do not interact, they do not acquire mass. You might have heard about photon, energy packets of light. You might have also heard that photons are massless. Then you might have thought, how can a particle be massless? I mean like anything that we hear should have mass. But the thing is, photons do not interact with Higgs boson. So they do not acquire mass. That's the thing. Okay. So Higgs boson and Higgs field are those particles that impart mass to other particles. I mean like if we read the standard model of physics, we will come across, I mean like, newer types of subatomic particles like fermions, leptons, bosons, like that. Okay. So that's the thing. Okay. So I hope it is understood. The concept of length contraction also. Yes. Shri Naiki, is it understood? I mean like, the sun and all.
Yes, sir. Yes, sir, I understood. So what is quarks and all of the quark, fermion, electron?
Yes, yes. These are subatomic particles. So to understand about quarks, leptons, fermions, muons, etc., we need to read the standard model of physics. Okay. So maybe, yes.
Can we have a class on that also?
Yeah, definitely. I'll take a class and I'll help you understand about that. There is a standard model of physics where we discuss about all those things. Okay. So that's a higher level of thing. So initially we'll understand the basic things, then we'll understand about higher things also. So that concept is clear. Okay. You may come across new facts from newspapers and all. But the thing is, if you have the basic concept clear, you will be able to relate with them. Okay. So time dilation we have understood, length contraction we have understood. Then third thing is mass energy equivalence. Okay, another thing is there, that is mass energy equivalence. So Albert Einstein has given a very, I mean like, popular formula which is equal to mc square. We all know this equation, right? But many of us may not know where it is connected, how it is beneficial, I mean like, with which it is connected. We all know that this equation is there, equal to mass mc square. So basically, Albert Einstein says that a small amount of mass can be converted into a very high amount of energy. Mass can be converted into energy. Energy can also be converted into mass. Okay. For example, just now we discussed about Higgs boson. So when they interact with other particles, they impart mass to them. So energy is somehow getting converted into mass. Then we also talk about, let's say nowadays, we have various types of nuclear power plants. Nuclear power plants are there. We have a small amount of nuclear fuel, and that small amount of nuclear fuel is able to provide power, right? For years, 2 years, 3 years, 7 years, like that. Okay. How that small amount of, I mean like, nuclear fuel is able to generate that huge amount of energy, right? It is able to generate because mass is getting converted into energy. Okay. Mass is getting converted into energy. I mean like when World War II was happening, the World War II ended because of atom bomb. You might have heard about fat man, little boy kind of thing, Hiroshima, Nagasaki. So they have dropped atom bomb over there. So atom bomb, I mean like there, I mean like nuclear chain reaction happens, and that is known as uncontrolled nuclear chain reaction. Uncontrolled nuclear chain reaction gives rise to bomb effect of, I mean like like Big Bang type of thing. Then controlled nuclear reaction, chain reaction happens in a nuclear power plant. Okay, so we control it through kind of control rods. So we kind of there are atoms, big atoms are there. For example, plutonium, you might have heard about plutonium and other kind of nuclear fuels. So what we do, we bombard those nuclear fuels with neutron. Neutron strikes them and they break into, I mean like one big atom breaks into two smaller atoms. When this big atom is bombarded with a neutron, when this neutron strikes, then this big atom I mean like divides into two smaller atoms, and it further gives rise to three neutrons like that. 1, 2, 3 like that. So this reaction is known as nuclear reaction, where an atom is getting converted into other types of atoms. Bigger atom breaks into smaller atoms like that. So this is nuclear reaction. So this nuclear reaction happens in nuclear power plants. In India, we have, let's say, like pressurized heavy water reactors. We have different types of nuclear power plants in the country. Okay, and we are trying to acquire small modular reactors in the country. Okay, we'll discuss about small modular reactors also in the coming classes. And apart from this, let's say like so we have 3-stage nuclear power program in India. So we are like currently we are operating in the first stage itself. Homi Jahangir Bhabha, I mean like he has talked about 3-stage nuclear power plants in 1950s. And since then, we have been trying to develop, I mean like, second stage of nuclear power plant, where, I mean like, kind of, we are going to operate plutonium-based reactors. Then, in India, we have huge amount of thorium reserves. Thorium is a kind of nuclear fuel. But we do not have the reactors that can utilize the thorium. So, we want to develop those reactors that can utilize thorium, and we will be self-sufficient in nuclear power capacity generation in India. Okay, that's the thing. So basically, mass energy equivalence talks about that a small amount of mass can be converted into large amount of energy. Then energy can also be converted into mass like that. Okay, so this is, I mean like so this is about this particular thing. Okay, spatial theory of relativity. All right. So is it understood? These are very important things. Then there is another thing that says relativity of simultaneity. Okay. So the events that may be simultaneous for one observer. Let's say I'm an observer. An event is happening here, both the events are happening together, so it is simultaneous for me. Both are happening together. But there can be some other, I mean like observers, for them these two events may not be simultaneous, because we will discuss that like time is a relative concept, space is a relative concept. Okay, space and time is a relative concept. So Albert Einstein has talked about it. Okay, so I hope that is understood. Spatial theory of relativity. So spatial theory of relativity was given by Albert Einstein in 1905. It has two postulates. What are two postulates? That like the laws of physics are same for all observers which are moving at uniform speed with respect to one another. This is first postulate. Second postulate is that the speed of light is same in vacuum, irrespective of the movement, irrespective of the speed of the observer or the source of light, like that. Okay, so this is a spatial theory of relativity. Having understood this, we will now move to general theory of relativity. Okay.
One example of relativity of simultaneity.
Relativity of simultaneity. It is, I mean like, for example, let's say, I'll talk about this. We are sitting on Earth, right? We are sitting on Earth. Now, there can be some incident happening somewhere at a particular point of time for me. There is another incident happening at some other place at the same time for me. So, these two incidents are simultaneous. Simultaneous means they are happening at the same time for me. But whether this incident will be same, whether these two incidents will be simultaneous for another observer, it is not going to be. Albert Einstein says that this is a relative concept. Space and time is also a relative concept. Okay. When we read about the second, the general theory of relativity, then we are going to discuss about space-time fabric. Okay. And how general theory of relativity is different from a special theory of relativity is that in the general theory of relativity, Albert Einstein also accounts for acceleration and gravity. In the first, a special theory of relativity, he does not account for acceleration. He accounts for uniformly moving objects. He does not take into account the concept of gravity over here. Okay. But in general theory of relativity, these two things are also considered by him. He has explained these two things also in general theory of relativity. Okay. So what happens in general theory of relativity? Some other things happen. So to understand about it, do we understand what is a fabric? Let me first write down the theory. General theory of relativity.
So when we say speed of sound is constant irrespective of the motion of the source of light, so the source of light motion, we say it's constant, no sir. But how do we say it? It is not constant, sir. Like we said, speed of light in vacuum is constant irrespective of the motion of the source of light or observer. So how do we different?
No. Albert Einstein is considering this. Albert Einstein is saying, he is considering that if these two conditions are met, then this is going to be the case. Okay, postulate means he is presuming these things. He is presuming. So far, huh?
No sir, the motion is constant or it is not constant, I'm asking.
See, to make you understand about this, I will have to give you an example, right? And you will be clear about that, okay? That speed of light is not always 3 into 10 raised to power 8 meter per second. I'll tell you how it is, okay? Let's say C is equal to 3 into 10 raised to power 8 meter per second. This is what I said. This is true for vacuum. What? This is true for vacuum, means outer space. But the thing is, you might have heard about this glass slab, an experiment of glass slab where we send a ray of light like this, right? This ray of light should go in this way, but it bends towards the normal, right? Then it should go in this way, then it bends away from the normal, like that. We might have seen this particular thing in our 12th standard NCERT or maybe in 10th standard NCERT also. It is about, this is a glass slab. On tabletop we have glass, thick glass, right? So this ray of light, it is moving, and why the ray of light is bending? This phenomena is known as refraction of light. Like bending of ray of light is known as refraction of light. When light moves from one medium to another medium, right, the speed of light changes. Basically, when we talk about, this is air, air means optically rarer medium. So here maybe speed of light is very close to C, which is 3 into 10 raised to power 8 meter per second. And if it is, let's say, water, it may be 1.5 into 10 raised to power 8 meter per second. Little less than that. Okay, so because this medium, glass, is an optically denser medium as compared to air. Optically denser. Optically denser means it allows the ray of light to move through it, right? There are opaque medium also. If I, let's say if I put light over here, it's not going to pass through this particular wall. Okay, why? Because it is an opaque medium. Some of the light may get reflected back, right? But it is not going to pass. So optically, these are known as optical medium. So experiments are done in 10th standard book or 9th standard book, where let's say kerosene is there, water is there, then like we have thinner is there, turpentine is there, I mean like lot of medium, glass is there. So then they do this experiment to understand what will be the speed of light in different medium. Okay, so when the ray of light is moving from a optically denser medium to an optically rarer medium, then the ray of light is going to bend towards the normal. What is normal? Normal is a line that makes 90 degree to this surface. Okay, so it is, this ray of light should go in this direction, but it is bending towards this particular line. So that is bending towards the line. So why? Because its speed has reduced. Then again the speed increases. So that's why it happens. So speed of light is not same in all mediums. But what Albert Einstein has said, he has considered that let's consider that the speed of light is going to be 3 into 10 raised to the power 8 meter per second in vacuum. So he has considered, postulated, means like he kind of presumed that this is the thing. Okay, but the speed of light varies in different medium. That's the thing. Okay, so is it understood?
Yes, so he considers it that the speed of light is constant.
Yes, yes. I mean like speed of light has been experimentally found that this is the value. I mean like this is the value. And they have done multiple experiments with other medium and they have identified what is the speed of light in different medium. That's the thing. So now here we talk about general theory of relativity. Okay, general theory of relativity. How general theory of relativity is different from special theory of relativity? It is different because of two things. Number one, he takes into account acceleration due to gravity, acceleration also, and he takes into account the gravity, concept of gravity as well. And he explains the concept of gravity differently. How he explains? So he says about a concept, and this is known as fabric of space-time. Fabric means clothing, like this is a fabric like that. So he says that like in the universe, space and time are closely interrelated with one another. Space and time are closely interrelated with one another. And here we can relate back to Big Bang theory. Why? Because like someone has said that once upon a time there was no time. Okay, so when we talk about this particular thing, Big Bang theory, so we say that Big Bang has happened. After then, let's say like things started taking shape. After then, time is counted. Okay, which is, I mean like it has been 13.8 billion years since the Big Bang has happened. 13.8 billion years since the Big Bang has happened. So when the concept of space emerged, concept of time also emerged. Space is expanding, right? Time is also increasing, expanding. Are we understanding? So here what Albert Einstein says that like basically if you know all of you is like Newton has talked about gravitation. What he has talked about? Gravitation. So he says that every object in the universe attracts every other object with a force which is equal to, so when we talk about Newton's law of physics, so he says force is equal to G into m1 into m2 upon r square. So he says every object in the universe attracts every other object with a force which is equal to G m1 m2 upon r square. There is some value of G which is known as proportionality constant. If this value is not there, so F will be proportional to m1 into m2 upon r square. To remove this proportionality constant, he has come up with G. There is a value, a specific value to it. So basically here we consider that all masses have a tendency to attract one another only. They do not repel one another, like that, he says. Okay, I mean like not about magnetic things, but in general about masses. All objects in the universe attract one another with a force. But Albert Einstein explains that how this attraction works. I mean, Newton has said that objects are attracting one another, but he does not explain further that how it happens. He says that attracts, okay. Albert Einstein says, explains that how it happens. So he says that the universe is made up of a space-time fabric. I mean, like, in the entire universe, such kind of fabric is there, which is a space-time thing, okay. Now in this fabric, let's consider, I mean, like, I have a net means a similar cloth. I have tied this net, one point here, other point here, other point here, other point here. Like two people are there, we have kind of, hold it. Now, if I put a mass on the top of it, mass means a ball of 5 kg. Net we have held. Now, if I put a ball on the top of it, which has a weight, let's say 5 kg and all, over here, what's going to happen? Means the space-time fabric is going to bend. It's going to bend. I mean, like, so if it is, for example, if it is looking like this, at this point, if from side, if we are seeing that from side, if it is looking like this, maybe, okay, if it is looking like this, or if it is from side, if it is looking like this, but after we put some weight on the top of it, okay, it's going to bend like this. So on that particular net, what we have done, we have put in a ball over here, and because of that ball, this net that we have held, so it has bent. I mean, like, net has similar structure as before. I mean, like, a structure in the sense they have cross sections like this, okay, they have cross sections like this, but the thing is it has bent, okay. And again, if I put a smaller mass over here, I mean, like, this was a bigger mass. If I have a smaller mass over here, it is also going to bend. It's going to bend little bit, okay. It depends on this weight and size of the mass, okay. It's going to bend little bit. Are you understanding? I mean, like, bigger mass, it's going to bend more. Smaller mass, it's going to bend less. Still bigger mass, it's going to bend more. This way, okay, like that. So he says that the heavenly bodies that are there in the universe, heavenly bodies means planets, sun, stars, right, moon and all. These objects are located on the fabric of space-time. Since they are located in the fabric of space-time, now what will happen is that, like, if we go back to the, let's say, previous diagram, if we go back, so we have put in one mass over here. It has bent a bit, we have put in another mass, we are putting another mass, okay. So what's going to happen? The bigger body, I mean, like, warps the space-time, I mean, like, bends the space-time more. This is known as curvature in the space-time fabric. So it is creating more curvature in the space-time fabric, it is creating less, it is creating less. Because it has created more curvature, so smaller bodies are going to get attracted towards the bigger bodies. Are we understanding what is happening? Bigger bodies have created more curvature, smaller bodies have created lesser curvature, and smaller bodies are going to move towards the bigger bodies because it has created more curvature. That's the thing. So he explains this way, and he says this particular thing is space-time fabric. Space-time fabric. Okay. Then these bodies, what they create curvature in the space-time fabric. Are we able to relate now with this, that what is a space-time fabric? So it is imaginary, okay, it is imaginary, space-time fabric, because it is not visible in the space in this yellow color, red color, blue color, But the thing is, like, it is considered that in the universe, I mean, like, fourth state of matter exists. What is the name of it? Ether.
Plasma, Bose condensate.
Plasma. I mean, like, it is also known as ether. Bose-Einstein condensate is fifth state of matter. Okay. So, fourth state of matter exists in the universe that way. Okay. So, this is the thing. So, three states of matter, solid, liquid, gas, we already see. So, they say that in the entire universe, ether is there. Now, the thing is, like, after some time, we will also understand that in the universe, I mean, like, some objects are visible. There are many objects that are not visible to us. Okay. Many objects are visible, many objects are not visible. Why it is the case? I mean, like, how things are visible. Things are visible because they interact with electromagnetic waves. You are seeing the things using the help of light. Light means, I mean, like, we are seeing white light. Whenever white light is falling anywhere or light is falling on anywhere, it will be visible to you. If no light is falling, it will not be visible to you, right? So anything that interacts, I mean, like, these objects are interacting with light. Interacting in the sense, like, they are either reflecting light, they are absorbing light, or they are refracting light. They are doing something with light when light is falling on them. There are objects in the universe that do not interact with light. I mean, like, they are not affected by presence or absence of light. Means, like, our source of inferring the thing is through electromagnetic waves. And those things that do not interact with electromagnetic waves are not visible to us. Okay. Kind of black holes, we can say. But scientists have come up with further refined theories. They say black holes are very, I mean, like, dense bodies that attract everything that is near to them. Okay. Even ray of lights are attracted towards it. They even cannot escape if they come in the range of the black hole. Okay. So that's why black holes are not visible to us. Why? Because when a ray of light goes, it gets attracted. I mean, like, it is absorbed like that. So in the universe, there is a concept which is, I mean, like, dark matter, dark energy. Dark matter and dark energy, they are available in huge quantity as compared to visible matter. Visible matter, visible energy is very less, but dark matter is more abundance. Okay, it's like that. So here we are talking about general theory of relativity. Okay, here general theory of relativity. So what happens in general theory of relativity? Now he talks about 2-3 important things. I mean, like, many important things. One is equivalence principle. Effect of gravity are locally indistinguishable from acceleration. I mean, like, when someone is falling from top to ground, so he is under the influence of gravitational force. But gravitational force and acceleration, I mean, like, they are indistinguishable in this particular case. So it says, like, they are equivalence. Okay, means, like, this is the thing. Then curvature of space-time. I have also already said what is curvature of space-time. It is because of the presence of these heavenly bodies, they are creating curvature in the space-time fabric. Okay. Then what are the predictions? Here it talks about gravitational time dilation. Okay. It talks about light deflection. It talks about gravitational waves. Okay. And cosmological expansion. Okay. So let us discuss about these terms one by one so that, like, we can understand about it. Okay. So this is important. I mean, like, predictions and consequences. One of the prediction is gravitational time dilation. Gravitational time dilation. Write a sentence related to this quickly. So we are writing about gravitational time dilation. Write down. Clock runs slower in stronger gravitational fields. clock runs slower in stronger gravitational fields. Okay, so what do we mean by this? It means, let's say, if there is a clock, if this clock is put on the surface of Earth and the same clock is put on the surface of Moon or maybe on the surface of Jupiter, these bodies have different value of gravitational force. I mean, like, Earth kind of, puts around 6 times more gravitational force as compared to Moon, right? So the thing is, a clock which is kept on a field where more gravitational field is there, okay? So when more gravitational field is there, what's going to happen?
Slower.
Clock is going to move slower, okay? And if it is in smaller gravitational field, clock is going to run faster, okay? So now here you can consider, there can be a movie, maybe you might have seen. People residing on the surface of Earth, now they have moved to some other planet.
Lost in space?
Maybe. Okay, I mean, like, there are multiple movies, I have not seen much. Okay, so the thing is, like, the value of time that we see, right? The value of time will be different in different field. So this is known as gravitational time dilation. More gravitational field will be there. Okay, clock is going to run slower.
वहाँ पे एनर्जी का कोई रोल नहीं होगा।
कौन सा एनर्जी का?
जैसे यहाँ पे एक जनरल बात कर रहा हूँ प्रैक्टिकली, यहाँ पे जो अर्थ पे जो क्लॉक है, उसमें जो एनर्जी हम डालते हैं बैटरी वगैरह लेकर,
हाँ हाँ.
वो इस अपने स्टोर करते हैं।
It's not about only the battery. It's about not the battery. I mean, like, वो battery वाला concept नहीं है. It's about कि how the kind of, time is going to be perceived here and there. मतलब, you are on the surface of Earth, all facilities are there with you. How long you can live on surface of Earth? Then if you live on a planet which has more gravitational field, how long you are going to, you will be able to live? Like that. Less gravitational field, how long will you be able to live? That kind of concept. Here we are talking about time with that reference. I mean, like, this is just a correlation, but you can understand that thing. It's not only the clock is going to run slower. Are we understanding? It's a relative thing. I mean, like, instead of putting that battery and all, we can put this digital clock, let's say. It's going to take, but the thing is, like, how it is going to impact other things. Okay.
Contradicting the time dilation.
Hmm?
Time dilation भी जो भी आपने बताया.
Contradict?
वही स्पेस है, वो वाला है स्पेस वाला है, यहाँ पे जनरल।
नहीं, वहाँ पे ऐसा था, two bodies were there. So you are connecting this particular concept with Kepler's planetary motion, laws of planetary
Time
motion.
dilation आती है special theory of relativity.
अच्छा, स्पेशल थ्योरी ऑफ रिलेटिविटी. अच्छा, मुझे लगा केपलर वाले में भी ऐसा था. ठीक है. Theories of relativity, special theory. It is time is experienced differently for observer in relative motion. So that's related to motion, movement. If the thing is moving, one thing is, like, with reference to Earth, if I am on the surface of Earth, with reference to Earth, I am stationary. Earth के, हाँ? नहीं. Anything which is there on Earth, anything, like all of, yes.
Sorry, sir. Like, supposing a person on the Earth and Moon, the person who's on the Moon, the time will be faster, sir. Do you mean that? And compared to the Earth and Moon?
हाँ. In compared to Earth and Moon, we are talking about that way. Okay, means, हाँ.
Faster.
Yes.
For the person on the Moon, the time is going to tick faster.
Tick faster for that person.
Okay, sir.
Okay. Basically, like, Earth itself is moving, we know. Even Sun is moving. I mean, like, with reference to Earth, I mean, like, Sun is, we consider that it is stationary, Earth is moving. But with reference to universe, Sun is also moving because, like, things are expanding, right? But the thing is, with reference to Earth, we are stationary. On the surface of Earth, we are stationary because we are moving at similar velocity as Earth. Relative motion is zero, kind of, if I am standing here. But I am going to perceive time, right? At Earth, somehow, I am going to perceive time, means, like, how the time is passing for me. If the same person from Earth, I am going to go some other planet, to some other planet, I am residing over there. how the time is passing over there with respect to me, it is going to be different. It depends on how much gravity that planet has. I mean, concept is that way. Okay. Okay. So this is known as gravitational time dilation. Apart from this, okay, there is another related concept which is known as light deflection. Okay, light deflection. It is simple. Okay, you might have come across many articles also related to this. Light deflection. Have you heard about one thing which is known as gravitational lensing?
Gravitational lensing, sir.
Hmm.
So in relation to instance which are time.
Have we heard about this term gravitational lensing? हाँ, yes. हाँ, आप बताइए.
सर मैं कह रहा था कि in relation to means कोई सन डाई कर रहा है in this relation में means सन dwarf star में change होगा ऐसा कुछ.
नहीं.
उसका नहीं रिफ्लेक्स मतलब होता है लाइट का ड्यू टू द मास जो होता है उससे लिंक इसका है.
हाँ, basically what happens over here when we talk about light deflection, basically I mean like we consider, like generally we consider कि light is traveling in a straight line. ऐसा हम consider करते हैं up to 10th standard ये करते हैं. Later on when we come to 12th we also understand about wave fronts and all. Every new wave front is becomes a secondary wave front, becomes a primary wave front and all. They kind of that's a different concept. So here what we are talking about, light deflection is means, let's consider a light is coming. Okay, maybe light is coming in this direction. Then over here there is a body. Okay, it comes across a body like this in the universe. Body means heavenly body. Heavenly body means it can be planet, it can be sun and all. This light was coming in this direction. I mean like, you know, it could have gone here. I mean like if it does not strike, or let's say this particular light source is coming this way. But now what is happening, since this body is there, this light is going to experience some deflection. Why? Because some kind of gravitational pull will be there by this body. Some kind of, like we talk about black holes, that black holes attract even light. It does not allow the light to pass through it. I mean like, you know, everything it attracts. So over here what is going to happen, when the light comes over here, it's going to get deflected like this. Okay, it should have gone in this direction. Okay, but it is getting deflected towards the source, and then from here it is going further like this. Anyone who sees from here, anyone who sees this particular thing, let's say like I'm on earth and I'm receiving this ray of light. What I'm doing, I'm receiving this ray of light. So here light is coming, I'm receiving here. So I will consider from here that this light has come from here originally. I'll consider it might have come from here. ऐसा सोचेंगे हम? Because like we'll feel कि हाँ, it has come this direction. But the thing is, because of presence of heavenly bodies, the light, ray of light that is traveling, it bends. Okay. Since it bends, now let's consider there was a body over here, a smaller body. From here light is coming. I am seeing from here. Similarly, maybe like, you know, another light, it might have been going over here. But the thing is, since this light has also deflected and it has come to me like that. Okay, from here I'll think that like, you know, this particular body itself is very big. I'm seeing from earth, one ray of light came, another ray of light came. I thought ki ye jo hai, it is coming from a very big heavenly body. But like it was coming from a smaller body. This body actually has come across a heavenly body on its path. So light got deflected, right? This phenomena is known as gravitational lensing. Gravitational lensing means because of gravity of this particular body, ray of light is bending and it appears from the earth that that body is very big. Okay, it is known as gravitational lensing. It is a kind of concept in physics. Okay.
Sort of will it appear big, sir? I mean, from the viewer, you're saying, the viewer.
From the viewpoint of the viewer, he will perceive that this body, yeah, he will perceive that the body from where light came, it is very big. He will perceive, but it is not big. Why it is happening? It is happening because bending of light is happening. And since bending of light is happening, smaller body is perceived as bigger body, and that's why we call it as gravitational lensing. Lensing means, like, you know, we have lens, I mean, like, you know, specs, lens is there na, in spectacles. Smaller thing can also be seen now clearly. I mean, it depends on the kind of lens that I have. Okay, I have concave lens, so now I am able to see far away things also. Okay, like that. So gravitational lensing actually, like, you know, the observer sees that the other body is bigger, he believes it, but actually it is smaller. This phenomena is known as gravitational lensing. And light deflection means light rays bend when they pass near massive objects due to space-time curvature, confirmed during solar eclipses. I mean, like, you know, this is what it happens. Okay, so if you want to write, you can write down a sentence related to it. So it says light rays bend when they pass near, light rays bend when they pass near massive objects due to space-time curvature. Okay. Then another thing is there, and it is also very interesting. So it is gravitational wave. I have also already explained gravitational wave. Gravitational waves. Now, what are gravitational waves? So what happens? Now, we know about our sun. Let's say this is the sun. Okay. On the surface of the sun, huge amount of nuclear reactions are happening every day, every second, all the time, right? Nuclear reactions are happening. What is happening? Because of these nuclear reactions, sun is losing energy every time. I mean, like, you know, nuclei are coming, they're merging, energy is lost, and that energy is emitted. I mean, like, you know, we are receiving all our energy from the sun. Okay, if sun was not there, then the earth would have become a icy planet. If sun is not near in habitable zone, this is known as habitable zone. Okay, so earth is at a habitable zone with reference to sun. If earth would have been very far away from sun, we have been so cold. I mean, like, you know, the entire earth could have been covered by ice sheet. So if it had been cold, then like life form would not be possible, right? The way that we see here. So on the surface of sun, huge number of reactions are happening at all point of time, and sun is losing energy. There will be a time when those materials that are reacting, I mean, like, not all the materials would be reacting and emitting energy. Some materials, I mean, like, you know, hydrogen are coming together, helium is forming. So when those materials are going to get exhausted means jab khatam ho jayega, then what will happen? This, I mean, like, all of these things are going to collapse. Abhi, because of huge number of reaction, it is kind of, that is happening, it is going to collapse. And after collapsing, all these things will come closer. Then it is going to form a black hole. So all the black holes that we see in the universe now, all the black holes that are there, these are remnants, means like remaining parts of earlier stars. I mean, like, you know, massive stars. Big stars are there. We name different stars differently. We have supermassive stars. We have neutron stars. I mean, like, you know, these are big stars. Much larger. I mean, like, thousands times larger as compared to the size of the sun. Maybe millions of times larger than the size of the sun. So when those big stars run out of energy, okay, so they collapse and they form black hole. What? They collapse, they form black hole. So when they collapse, they form black hole. There is still going to be an object in the universe. The objects are going to come closer. It is going to be highly dense. I mean, like, density will be very high. We consider the density to be infinity. Okay, infinitely dense object. Okay, and very high temperature will be there. So those kind of objects are going to kind of, create very huge amount of curvature in the space-time fabric. Okay, they are going to create huge amount of curvature in the space-time fabric. Okay, and there will be a point over here, that point will be known as singularity. Okay, so let me make it some other color. That point will be known as singularity. Okay, I mean, like infinitely dense object, it is maybe very big also, but like it is going to do huge amount of curvature in this space-time fabric. That's the thing. So how black holes are formed? When stars run out of energy, when they collapse, black holes are formed. And when two black holes merge together, one black hole, other black hole, they came in gravitational contact and they are going to collapse. When they collapse, they are going to release some kind of waves, and those waves are known as gravitational waves. So Albert Einstein predicted that gravitational waves exist. He predicted this in 1915, and in 2015-16 people have done experiments, and those experiments are done through detectors. One of the detector is known as LIGO detector, laser interferometer gravitational wave observatory, and Virgo detectors. Okay, so these are detectors to detect the presence of gravitational waves. Okay, so this is the thing. Is it
The black hole, they initially form, sir, like they come near the sun, sir. The black holes. When
okay?
they run out of energy.
Can you please repeat the question?
No, sir, the black holes you said, no, sir. Like sort of when will they come towards the sun? I mean, sort of, you said they come towards the sun, no, sir.
No, basically like all planets, all stars are located very far away from one another. They are, I mean, like, billions of light years away from one another. Okay, so it is not the case that like, I mean, like, other star is approaching towards the sun. It may be possible that they are approaching, but like it is not going to approach in our own lifetime. I mean, like we have a very shorter lifetime, and like the universe has billions of years of lifetime, like that. Okay, so the thing is like, after a large amount of time, I mean, like now let us consider, let's say like, there are two stars, a small star is there, a big star is there. So where we are going to have more number of reactions, I mean, like faster reaction, huge amount of reaction, bigger star. If we have a bigger star, huge reaction is there. Okay, so it's going to collapse soon. Why? More number of reactions are happening. Smaller stars generally have more lifespan as compared to bigger stars. Okay, although we have not yet studied about black holes and all, I am going to discuss about black holes, but like we are in a stage where like we will be able to solve questions that like, I let's say took in the beginning. Now we are in a state to solve these previous year questions. One of the question is this question. It says, recently scientists observed the merger of giant black holes billions of light years away from Earth. Two or more than two giant big size black holes, they merged, and these black holes are located billions of light years away from us. I mean, like very far away. What is the significance of this observation? Okay, they have given four.
Option B, sir.
Option B. It says gravitational waves were detected. Okay, I mean, like through gravitational waves, if we have detected gravitational waves, it means we have inferred that black holes might have merged. Okay, this is the thing. So Albert Einstein said this thing in his general theory of relativity in 1915. In 2015-16, gravitational waves were detected for the first time. Okay, and then in 2019, UPSC has asked a question. Okay, and on that topic, Nobel Prize was awarded. Okay, so the thing is, the Nobel Prize that were awarded in last 2-3 years, they are very important. You need to connect those topics in a manner that like you have clarity of the topic. When you have clarity of the topic, you will be able to solve such questions. Okay, Now we have another question, this question, okay. We'll read this question, what it says. Giant stars, we understand stars, sun, I mean like anything similar to sun, they are stars. So giant stars live much longer than dwarf stars. No. Giant stars die soon, okay. Compared to dwarf stars, giant stars have greater rate of nuclear reactions. This statement is right, this statement is wrong. So yes.
Why they die so, sir? Because of the energy created?
Because of the energy that is lost, okay. I mean like giant stars, huge amount of nuclear reactions happen, they die soon as compared to smaller stars. I mean like our sun is one of the smallest stars in the universe, okay. Other stars are much bigger, okay, millions times bigger as compared to sun, kind of. So it is, statement 1 is incorrect, but statement 2 is correct, option D.
When fuel is finished, then
Yes, if fuel is finished, then everything gone.
Petrol is finished.
Huh?
Sun's petrol is finished.
Like, yes. So Sri Nike, yes, you are saying something.
Case I must be. So sun.
sun case.
So why has sun not kind of, died out so like this?
It is dying, every day it is dying, but like it is still have lot of energy. I mean like lot of material to do those reactions. Slowly and gradually it is dying. There will be a day, I mean like, in future when we will not be there, that sun will die.
Okay, sir.
That way, okay. So I hope like we are able to solve these questions, and we are also able to connect that where these questions come from. I mean like, how these questions are related. So we need to have clarity of the concept, and we'll be able to solve questions, any type of questions, okay. So this is the thing, gravitational waves. Then cosmological expansion. So general relativity provides a framework for understanding expanding universe, leading to insight about cosmic evolution. So we already know that the universe is expanding, and for that we have studied about the Big Bang theory, we have studied about Hubble's law also, we have discussed about, I mean like, the laws of planetary motion as well. So a lot of things we have covered, okay, today. So today it was just an introductory lecture, so that like you understand how the science and technology class is going to be, okay. So tomorrow we are going to discuss many more topics which are important for the exam, and also I am going to give you a lot of questions also, okay. I think 20 questions are given every day, right, to you to solve. So today I have not come up with questions, tomorrow I'll give you the question, okay, questions will be ready. And also, let's say notes will be provided for every lecture. There can be some notes for which, let's say, there is no time to cover it in the class, but after the class, anytime you want to discuss with me, you can always connect with me, okay. So that way I'll be kind of, available. So my email ID will be there with you, WhatsApp number will be there with you, okay. My name is Jahidul, some of you may be knowing me, some people do not know me maybe, okay. So, yeah, I'll share my email ID, yeah. I'll share my email ID and WhatsApp number also. This is my email ID, and this is my WhatsApp number. If in case you have some doubt related to any topic, just you can ask me that question there, or you can kind of share photo of that topic, maybe anything that you want to share, okay. Yes, 9310727976. Yes. So my email ID, some of you already have it, right? So we have been in touch, and then WhatsApp number is also there. So now, before we go, I mean like I think like class is taken up to 5:30 or 5:30. Okay. Okay. So before we go, I just want to take your feedback. I mean like, was the class very slow or very fast? what you found?
So the topics were made clearer, sir.
Okay, yeah, that's a good thing. Okay, so if we understand the topic, अच्छा,
फर्स्ट डे है तो
हाँ,
कहीं टॉपिक
I think current affairs go by the top. If you don't understand in depth, sir,
concept clarity हो रही है लेकिन
after the class.
okay, so he says it can be made little faster also. And Shinaiki, yes, so you said something.
Yes, sir. No, so usually when we do the current affairs for science and technology, I don't usually understand the depth of the topics. Like say what is black hole, singularity, and all of that. But today I got a clearer understanding after the class, sir. What is exactly what?
Okay, that's a kind of compliment for me. Thank you so much. So we have not yet covered black hole. We have kind of made the situation that now if we read black hole, we'll be able to understand. Okay, huh?
Thank you, sir.
Yes, yes. All right, huh? Thank you so much. So like we'll have a class tomorrow also, and so this note will be uploaded on the portal, I think. Okay, Shinaiki, I hope you might have gotten the note by now. I'm not sure.
अपलोड होता है पोर्टल पे
Okay. Yeah, it is uploaded on the portal. It is already given in printed format to the people who are here, but it is uploaded on the portal also. And tomorrow we are going to discuss many more topics. All right. Okay then. Thank you so much. Thank you.